Hi friends, is my voice is audible to you? If my voice is audible and if everything is fine, please let me know, right? Hope all my brothers and sisters are doing good, right? Okay, let me just start the session, bros. Okay, okay, coming to today's session, the session is all about moment distribution method. I hope you already know that, right? It's a mega mock, it's a marathon today. So we will completely work out all this moment distribution method for today, right? Right. Okay. One second. Let me just check how many of you people are in online. One second. Let me just check. What happened with this? Okay. Okay. I just want to know is uh, is my voice is audible and is my display is visible to you? Vasant Sai, is my display is visible to you? Okay, is the display is visible to you, Vasant Sai? Right? Dear Vasant Sai. Yes, sir. Okay, okay. Right. Okay, okay, okay. Good, 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 good. If my display is visible to you, then it is fine. Okay. Right. Okay. So let me start the session, bros. Okay. Coming to today's session, it is all about marathon on a moment distribution method. Right. One second. Mhm. Right. Yes. It is marathon and moment distribution method. Okay, right. Today we will work out all the framed structures by using moment distribution method. Okay, and coming to before I start the session, I just want to say a very big hi to all of you guys. Okay, so welcome to India's largest online e-learning platform, Unacademy. A very big hi to all of you who are in the online. If you are in online, please say yes, hi. Okay, right. And one more thing also, I just want to convey like. Before I start the session, I can recommend you to install the Unacademy Learning app. Install the Unacademy Learning app and keep your target as GATE and ESE. And in the search button, you can type my name Venkata Tilak to follow me, right? And moreover, I just want to convey one more thing also. If you are a serious aspirant of GATE and ESE or any other competitive examination, bro, definitely I can say like I can recommend you to take the subscription. The prices are going to get hiked from tomorrow onwards. I can recommend if you are a serious aspirant, if you are really interested to crack a GATE, ESA or any other competitive examination, I can recommend you this paid codes by taking subscription. Use this code VT10 to get 10% discount directly on all courses in an academy platform. Right. So some people will say like Vasant Sai will say like, sir, please introduce yourself. I am Venkata Tilak Uppalapati. People call me as Venkata sir. Some people call me as Tilak sir. I completed my master's degree from University of Sheffield, England, and about to complete my doctoral degree also. As my background of education is completely into structural engineering, you can also see I am going to teach only the structural engineering subjects in here also in an academy. My subjects I will deal are ranging from engineering mechanics, strength of materials, structural analysis, concrete structures, steel structures, and finally to construction materials and management. Totally, the six subjects I am going to deal here. Some people will also ask us, "Sir, what you had done in your previous." What you had done in your previous years. Previously, I worked as research scientist in University of South Carolina. In this is in USA for a funded project. I worked as a team lead also for that project, and moreover previously I worked as head of the department of civil engineering also in an engineering college. uh, that means I have both global experience and local experience. In addition to this one, totally I have 12 years of teaching experience in teaching GATE and ESE for different coaching institutes all across India. uh, in addition to teaching, some people will also ask us, do you do any other thing as far as engineering side? Do you do? Yes, I do. I personally do consultancy. I being a structural engineer, I personally do structural design consultancy on my own. I provide to my clients structural drawings to my clients. I provide, and I provide moreover material testing reports also to my clients. This is my brief background. Hi Prashanti School, how are you? Hope you are fine, right? And some people will also ask us, sir, okay, you asked us to install the Unacademy learning app, so how to do that? So go to the Play Store. I hope everybody has smartphone or maybe anything, maybe iPhone also. Go to Play Store or App Store. In that App Store, please type this name Unacademy learning app. When you type this name Unacademy learning app, definitely this type of championship trophy will be visible to you. Please install. If you install that app, then definitely you are able to see this type of screen. I hope you are able to see this type of screen, which is on the right hand side. In that right hand side one, keep this goal. This is the goal what you want to achieve. Maybe you can keep the banking sector, maybe you can keep the GATE and SSC or maybe you can keep other PSU examinations, maybe you can keep the target examination you want to crack. There are so many courses are there ranging from 6th standard to 12th standard, 6th standard to PG standard. So you keep that target, and here in this one, I mean in this main menu, you please select the topic called, I mean there are so many things are there, but you select the name called free classes. In free classes, if you select from the main menu free classes, and in the search button, after you select free classes, from the search button you type my name, Venkata Tilak Uppalapati. When you type my name Venkata Tilak Uppalapati, then definitely my profile will be visible to you. When my profile is visible to you, you please follow. Some people will cry at me like, why we should follow you? What are the advantages in following us? Why we should? Yes, definitely. The advantages in following me are, first advantage, whatever may be the free content that I had already done for you will be visible to you. So I can say you are able to access all the free content. Access free content. And second thing, what is the second advantage? Second advantage in addition to this free content is the upcoming free lectures what I am going to take in app or in special classes will be notified to you. Notifications will come. After this, the third advantage, after each and every class, we will provide a PDF notes of each and every class. You can use that PDF notes also for free of cost, without using, without paying a single penny, right? And hope you can see from this one, you can see different things like mechanical engineering faculty full length courses. What are the different courses that are already there? You can do all this stuff. If you are a serious aspirant, you can take the subscription, and I can say use this referral code when you are taking subscription, brother. If you want to get 10% discount, the mandatory thing is you need to use this code VT10. When you use this code VT10, it will directly provide you 10% discount, and it will shows your trust on me also, and it will direct connect between you and me. If it is structural engineering background, I mean if it is civil engineering background, I will take care of your entire preparation if you use this code VT10, right? And one more thing also, some people will say, sir, what are the uses or benefits when I use this when I use the subscription? What are the uses? Some people will say like, sir, how to follow? Is there any other thing how we can follow? If you click on this link, you can directly follow me. That is one way, right? Now coming to the advantages of taking subscription. The first and foremost advantage is everyday daily live classes will be notified to you, man. I mean daily live classes. In addition to daily live classes, I can say like uh, instant doubt resolution is possible when if you had taken the paid subscription. That is the first and foremost advantage. Second advantage is to crack any sort of competitive examination, uh, you should have a support of test series. Even in an academy, we are providing the support of test series in terms of daily wise tests, mock tests, grand tests, etc. And you can evaluate your performance. After you evaluate your performance, you can understand at what level you people are when compared to topmost students of an academy, right? And if you want to improve your performance in some of the areas in terms of marks or in terms of concept in some of subjects, right, you can definitely do that by understanding your performance. That is the second advantage. Third advantage is there is no need to plan yourself. We will provide all the plan. All the courses that are provided by Unacademy are completely structured courses. We will provide the plan. You need to follow the plan. If you stick to the plan and if you are able to work out all the problems, and if you are able to listen to the lectures carefully within the scheduled time, definitely we are pretty much sure like you are able to crack any sort of competitive examination with very pretty good rank. That is for sure. That is the third advantage that we can say. Coming to the fourth advantage, let us suppose Prashanti school is not able to come down to a class on one day. In such case, he or she will be provided with the same access of lecture, maybe in terms of offline. In terms of offline, maybe through maybe through a mobile phone, maybe with the help of a smartphone, or maybe with the help of a tab, or maybe with the help of a PC, depending on his or her comfort. The recorded version will be provided to them, right? So that is the greatest advantage. Because of domestic works also sometimes you may miss. In such case, the recorded version is also available to you for n number of times within the duration of subscription that you had taken. These are some of the topmost educators that we have, brother. Okay, you can watch these educators names and all this stuff directly in an academy. Okay, and I can say one more thing also. Use this referral code. If you are a serious aspirant, use this referral code VD10 to get 10% discount, and you can follow me by using this link. These are also some of the topmost indicators. And I can say one more thing. The classes will be held separately in English and also in Hindi medium. So depending on your requirement, you can go to any sort of the class. You can watch any sort of medium class that you want. Okay, right. And let us, some people will also ask us, sir, till now in GATE and ESE, how many courses you people had launched? In GATE and ESE, till now we people had launched till now 7 courses in civil engineering. Till now we people had launched, right? And as every month one more course will definitely get added, as pool of faculty is going to get increased, and the number of courses will also get increased month by month. You can expect more number of courses. Out of these 7 courses, few courses are in English medium, few courses are in Hindi medium, few courses are long term courses, few courses are short term courses also. So you will, when you have taken the subscription or paid course, you will be provided with access to all the courses, when compared to the free users. When compared to other platforms, you will be provided with all the courses access. And you can use the same code VT10 to get 10% discount, uh, to uh, to to get the subscription, right? And I just want to say, from tomorrow onwards there is a big price hike is happening. That price hike is effective from 20th September. So today is the last day for the least amount, I mean. So I can recommend you guys, like, so just before 20th September, before 20th September, like till today, the prices are like this. And after this 10% discount, if it is a 12 months course, it is to 22,500. If it is a 24 months course, it is 27,000. But if you are a student, if you will take the subscription after 20th October, in such case the prices hikes are almost 47%. So please be aware. If you want to take, really, if you are an aspirant, I can recommend you to take care today itself. Okay, and use this code VT10 to get 10% subscription, bro. When you use this code VT10, then you will get 10% discount. It shows directly your faith on me. It will directly connect between you and me, right? So this is also, I mean, the same thing. So before and after, only one day is left, I can recommend you. And 18 months before this one, 18 months course, there is not there. But right now we are introducing even 18 months course also. You can take even 18 months course also, right? I just want to convey, we already started 3 new batches, okay, in YouTube for free of cost, so that some of the content, like maybe the 30% to 40% thing will be definitely covered in detail. So in these batches, so I hope you can take it, you take use of these take use of these batches definitely. right? So let's crack I mean, subscribe to this channel, let's crack GATE and ESE. Definitely you are able to get too many notification, and you will get more of the free content. So here as a team we are working out all this for free of cost. So here as a team we are 12 faculty who are teaching here on this let's crack GATE and ESE YouTube channel, right? And every day my classes are by 9 p.m. Except marathons, okay? And I can say, right, shall we start the session, brothers? Okay. So I just want to convey first what is moment distribution method. There are two different methods are there. One is a force method and second one is a displacement method. This moment distribution method comes under the terminology called as displacement method. Another name for this displacement method is also called as equilibrium method, I can say. Another name for this displacement method is also called as stiffness coefficient method, because here we will use the stiffness of the elements in working. Here we will use stiffness methodology in working out the displacements of unknown joint displacements. So that's the reason why we call it as stiffness coefficient method also. And it is an approximation method, or it's a trial and error method also, we can say. That's the reason why we can call this moment distribution method, I can say this moment distribution method can also be called as successive approximation method also. Successive approximation method. Now everybody will say like, sir, in this moment distribution method what you will do? This moment distribution method is useful to analyze indeterminate framed structures. Why this method is used? The answer is very simple. To analyze indeterminate rigid jointed structures. So this method is not applicable to analyze indeterminate pin jointed structures. So please be aware. So coming to validity of this method, so where I can use this method, coming to validity of the method, I can use this method definitely to analyze indeterminate. Please understand, you are able to use this method for indeterminate rigid jointed structures like indeterminate portal frames. Some people will also ask us, sir, what are the examples for this indeterminate rigid jointed frame structures? Maybe I can say indeterminate beams, indeterminate portal frames, indeterminate, I am saying portal frames, not pin jointed frames, portal frames, where the deformation of the structure is majorly because of flexuration, right? So coming to validity of this method, I just want to convey, there may be for every method there are definitely some limitations are there. So what is the first and foremost limitation? This is applicable to indeterminate rigid jointed structures. This is definitely applicable to rigid jointed framed structures, but without internal hinges. So this I can say invalid, this method is invalid for indeterminate structures with internal hinges. So whenever there is an a indeterminate structure with internal hinges, then this moment distribution method is not applicable. That is the first and foremost thing, that limitation that you need to understand. This is, we can call it as limitation, but can be applied to determinate structures with internal hinges, determinate rigid jointed structures with internal hinges, right? So is that okay? So I just say, if you are in online, please say yes, hi, so that I will also understand. You people are understanding this or not, right? And I just want to say validity of this method. Some people had a doubt like, sir, is it is valid only to prismatic sections or non-prismatic sections also it is valid? This method is valid even for members with different flexural rigidity. I mean to say this is applicable to both prismatic and non-prismatic structures also. Applicable to both prismatic and non-prismatic structures. So what do you mean by prismatic structures? If the cross section size is one and same at each and every point in the member, then in such case such structures, such members are called prismatic members. Non-prismatic sections, if the cross section size and shape is varying with respect to point, in such case such members are called as non-prismatic sections. Yes, okay, right. So for both of these things, this is practical, this is applicable. I just want to say this is a successive approximation method. Practically, maybe after I teach you, after the completion of this method, you will understand like this methodology is this moment distribution method we can practically stop when at a rigid joint, if the different if the balance of moments, if the balance in the moments is less than 10 percentage, it is less than 0.1, in such case we can stop this methodology, we can stop this method practically. So that's what I can say. So if I just want to write that one also, can I rub the screen, dear F2 Bindas bro? And can I rub this screen, dear Vasant Sai? Can I rub this screen? Right, so I just want to write that. Okay, I am rubbing the screen, brothers. Okay, so I can say like, if in any beam or structure or frame, you will see this is a trial and error method na, that the moment distribution trials, moment distribution procedure of trial doesn't end doesn't end doesn't end. Practically we can stop those trials. Practically we can stop those trials when the moment at a joint is moment at a joint uh, to be balanced is less than 10 percentage. Some people will say less than 10 percentages. So if at a joint, if we take, maybe I can say this, maybe b a b c. So at the joint b, if you are taking the if you are taking the equilibrium at joint b, if you write mba plus mbc, so moments of all the moments, the net moment at joint b is 0 na. So generally if you write mba plus mbc, it cannot always be equal to 0. If it is less than or equal to 0.1, then by that time practically you can stop this iteration. This is a trial and error procedure, so you can stop the iteration, brother. So I can say you can stop the procedure. So always for all the problems, moment equilibrium is not always 100% satisfied at a joint. So mostly like if it is satisfied like less than 0.1, right, then you can understand, you can stop the procedure. That I want to say. Okay, you will understand this procedure. By the time I complete this procedure, you will understand. Okay, now everybody will also ask us, sir, who is the scientist who had given this one? Professor Hardy Cross has given this procedure, and even Professor Hardy Cross has also given column analogy method also. But here today we are talking about moment distribution method. So before I teach you moment distribution method, I just need to teach you some of the definitions, right? Some of the basics. If you don't have that basics, you cannot progress well. You will not understand the moment distribution procedure. Now let me start from the basics so that we will talk. Okay, so coming to the first uh, right? So coming to the first and foremost, sorry, right? So okay, I hope you can take as a note this one. Eraser, 1 second. If you want, you can take a screenshot of this one, just like a small note. Okay, some people may ask us, or please provide a small note. So you, after explaining, some note is also required, then they can take the small short notes, a crispy one, not a lengthy. Okay, right? And okay, now let us move to the fundamentals. Is that okay? Can I move to the fundamental definitions before I start the moment distribution method? The first and foremost definition that is required is absolute stiffness of a member. 1 second. Ouch. So the first and foremost definition is absolute stiffness of a. There are 5 to 6 definitions are required. After the based on these definitions, also some of the questions were already asked. So let me start with the first and foremost definition: absolute stiffness of a member. So forget about the terminology absolute. So if you understand about the stiffness of the member, then you can work out. So what is absolute stiffness of a member? I can say, I hope if you write F is equal to K into X, then K is equal to stiffness, which is equal to F by X. It is nothing but force required to produce unit displacement, or force generated in displacing the structure by a unit. That is nothing but stiffness. So from this definition, I can write force required or developed to produce unit displacement. This is the basic terminology of stiffness. Generally we can write, but here the terminology is absolute stiffness. Uh, and I can say the force, how many types of forces are there? I can say generally I can say a point force is there and a moment force is there, and moment force. So coming to displacements, because of point forces, translational displacements are possible, right? Translational displacement, right, brother? And because of moment force, rotational displacement is possible. The type of displacement that will come into picture is rotational displacement. Now here I am talking about the stiffness, force and every stuff in terms of moment force and rotational displacement. So absolute stiffness, how I can define? It is the moment required to produce unit rotation. It is the moment required to produce unit rotation at the near end of the member. So I just want to write the definition. It is the moment. Maybe can I rub the screen before I write the definition? Is that okay? Ved Chinu Vasant Sai F2 Bindas. Okay, can I rub the screen just before I write the definition? Here this is the basic stuff to teach you. This is this small screen I opened. Okay, can I rub this small screen so that I will directly write this definition, right? So I just want to rub the screen first. Okay, the basic definition. So I can say is the moment required to produce, because of moment translation, because of moment rotational displacement is possible. The moment required to produce unit rotation at the near end of the member, is called absolute stiffness of a member. Now everybody will cry, sir. Okay, sir, we understand. We know the definition of moment. We know the unit rotation, that is unit slope. Some people will cry at me like, what is unit rotation? Maybe we can write the unit rotation as unit slope. In slope also we can write at the near end of a member. Now everybody will say also, sir, what is this near end? So this is the the point at which where you are applying the moment, that point is near end. So this is the point where you are applying the moment. Maybe that moment is m. The amount of moment m required to apply at the near end to produce a unit rotation. I hope clearly you can see this theta is 1. A unit rotation at the near end. In such case, that moment required is nothing but stiffness of the member, that is K. So this end where the moment is applied, that is called near end, and the at the other end of the member, this is the near end, the other end of the member is called as far end, right? This is far end. So I hope you can write like is called absolute stiffness of the member. I just want to say here, by the time displacement unit rotation is only possible here, it only unit rotation is allowed. It doesn't mean like even vertical translation is also allowed. No, we are not saying that one. I can say without translation, that is without sinking, without sinking, just only unit rotation is needs to be possible at a point. In such case, what is the magnitude of moment that is required to produce that unit rotation without translation, that is without sinking? That is nothing but absolute stiffness of a member. So coming to absolute stiffness of a member, this is near end and this is far end. When this, there are two different conditions are there. When the far end is fixed, I can say case 1. In this one, case 1, hi Anil Madriki, hi, hope you are fine, hi Ved Chino, hi Vasant Sai, hi up to Bindas, a very big hi to all of you. So this is the basic definition. Now based on this basic definition, when the end conditions, when these far end conditions are of different nature, when the far end may be fixed, when the far end may be hinged, when the far end may be, I can say, a free end. In such case, the moment required to produce unit rotation at the near end value will also get changed, right? So I just want to say like case 1. What is case 1? When far end is fixed. When far end is fixed, now when the far end is, I hope you can say, when far end is fixed, moment generally to produce unit rotation at the near end, when the far end is fixed, if you I hope you can directly work out m is equal to, you will definitely get 4ei by l is the stiffness, m is equal to k into theta, and to produce unit rotation, at the near end, okay, what is the moment that is required? That itself is nothing but the absolute stiffness of the member. So the absolute stiffness of this member when the far end is fixed, I can say is 4ei by l, because the theta value is a unit here. So it is 4ei by l. Now everybody will also ask us, sir, okay, when the far end is fixed, the formula or basics one we can write is 4ei by l. So what is ei? EI stands for flexural rigidity of the member. A stands for flexural rigidity of member. L stands for length of the member. Okay. Now everybody will also ask us, sir, when far end is fixed, okay, you mentioned. Now you people tell me, you please tell me when the far end is hinged, right? In such case, what is the absolute stiffness of the member? That is the moment required to produce unit rotation at the near end of the member in such case, right? So far end is fixed case. So you, when the rotation is a unit, right? Maybe I can rub this screen. Maybe I can write when the far end is fixed, when the value of this k is 4ei by l. Now the another case is, sir, when far end is absolute stiffness of member only, but when the far end is a hinged one, right? The second case is case 2, far end is hinged. This is near end, this is far end. When the far end is a hinged, I hope you are able to see, the far end is a hinged. By that time, how much amount of moment that I need to apply to produce clearly a unit rotation in the member at the near end? So in such case, the moment that I need to apply to produce unit rotation is less than when compared to the case 1, right? So the case 1, its moment that I need to apply is 4a theta by l, but in case 2, when the far end is hinged, it is that moment m is equal to k 3a theta by L and the value of theta is 1. So in such case that m value itself is called as stiffness of the member and the value of that k is 3a by L. So when the far end is hinged case, okay, we will write the absolute stiffness of the member is k is 3a by L. Now some people will also ask us, sir, when the far end is free, now I'm expecting answer from you guys. I hope this is near end and this is far end, and I hope you know far end is free, there is nothing. When the far end is free, you tell me how much amount of moment I need to apply at the near end. I am expecting answer from Anil Madriki, Vasant Sai, Ved Chino, F2 Bindas or any other person. When the far end is free, I hope far end is free, and the far end is free, at this near end how much amount of moment I need to apply to produce unit rotation. So that is the question that I am asking. So when the far end is free, there it will, I mean, this is already a hinge which allows already rotation, so I can say directly the moment m is 0, the 0 moment is required to produce unit rotation at the near end, because it will try to, it is an unstable structure, it will try to move in this way even without a small moment also. So I can say when far end is free, the value of that k, that is absolute stiffness of the member, is directly 0. Is that okay? The first definition is absolute stiffness of the member, right? Second stiffness is, some people will say like, sir, this the first definition is absolute stiffness, what is the second definition? Absolute stiffness of a member is the first definition, but second definition is absolute stiffness of a joint, a rigid joint, I just want to say, right? So can I go to that one? So can I deal with I mean absolute stiffness of a joint, is that okay? Right? Anil Madikri, Ved Chino, Vasant Sai, F2 Bindas, persons who are on the online. Can I move to the next slide? Right. So the next definition is stiffness of a rigid joint. What is stiffness of a rigid joint? How I can work out the stiffness of a rigid joint? See, you take a joint as a group, you take joint as a team. In a team, what is the strength of a team? Strength of all the members in the team is the strength of the team. The similar way, absolute stiffness of a rigid joint is sum of the absolute stiffness of all the members meeting at the joint. That is, dear Shebin Sailuddin, I will take definitely, brother, for two for I can say for this month it is, I am dealing with structure analysis and steel structures in app and structure analysis on this one. In the next month definitely I will take RCC. Don't worry, brother, please allow me some time. So everything will not happen in one day. Yes, let me complete this structure analysis, and after that I will go to RCC as per your words. Definitely before your GATE examination I will complete all the structural subjects. It is a pretty sure and it's a promise from my side. I swear you, I will complete all the structural subjects before your GATE examination. Okay, so please allow me some time. Okay, don't worry, Shebin Zailuddin. Okay, right. Okay, so because you should also understand, like, everything cannot be worked out. Rome was not built in one day. Similarly, all the subjects cannot be worked out in a single day. I know your enthusiasm, even I want to do, but time is the constraint. So please allow. Right. Okay, right. Yes, definitely I had that in my mind. I will first work out the important subjects or most toughest subjects I will tackle, and then finally I will move to the construction methods and management at the last. Okay, right. Shebin Sailuddin, brother. Right. So can you tell me what is the stiffness of a rigid joint, brother? So how you can define the stiffness of a rigid joint? Is there any idea? So coming to stiffness of a rigid joint, I can say is it is sum of the stiffness of all the members meeting at that rigid joint. It is stiffness of a rigid joint, which we people call it as sigma k. Sigma k is equal to sum of absolute stiffnesses of all members meeting at the rigid joint, meeting at the joint. Now you people tell me, I just want to know, I want to work out the rotation at joint O. To work out rotation at joint O, if I apply a moment M, okay, how you can write that that moment M is applied on joint O. So to that, so F is equal to K into X. Similarly, I can write that moment M is equal to the stiffness of joint O. What is called as stiffness of joint O? So it is stiffness of rigid joint O. So I can call it as sigma K of joint O, and it is rotation of O. We can write in this way. To work out rotation of joint O, the moment applied value will be known to us. Maybe we can work out on this rigid joint what is the net moment that is physically applied. And in addition to this one, what is sigma KO? Summation of stiffness of all the members meeting at joint O. What are the stiffness of members meeting at joint O? At joint O where the moment is applied, that is near ends, right? And these are all the other ends where these ends are far end. This is far end, this is far end, this is far end, this is far end. So how I can write sigma KO based on the stiffness of the rigid joint, sum of the absolute stiffness of all the members. What is absolute stiffness of joint O? Absolute stiffness of members joining at O. OA member, OB member, OC member, OD member. So I can write KOA, KOB plus KOC plus KOD. We can do in this way, right, brother? Now you tell me from your basics in your previous slide what I talk. What is the absolute stiffness of member OA? O is okay. What O is near end, A is far end. Far end is fixed. When far end is fixed, what is the absolute stiffness of that member OA? I can say when far end is fixed. You had already seen, which is 4 EI by L plus OB. Far end is, this is free. When far end is free end, what is the stiffness of the member? Generally we can take it is 0. OC is far end is fixed, right? For far end is fixed, the absolute stiffness of the member is 4, and EI is EI for this member only. EI is EI, there is no change, and the length of this member is L. What is the length of the member OC? Length of the member is L only. And for KOD, what is the absolute stiffness? The absolute stiffness of member OD. O is near end and D is far end. At far end it is hinged. Clearly you are able to see far end is hinged. And at far end is hinged, right? So what is the absolute stiffness? I hope you already know it is 3 flexural rigidity of the member EI of OD by length of member OD. So if you do in this way, definitely you will work out this 11 EI by L, right? So from this absolute stiffness of this rigid joint, right, some people from the fundamental definition, F is equal to K into X. So M is equal to K is for the joint, which is sum of the absolute stiffness of all the members meeting at joint O, stiffness of joint O into rotation of joint O. If I say the moment applied at joint O is M, what is absolute stiffness of joint O? Which is 11 EI by L, right? I can write in that way, and I can directly find out what is rotation of joint O. So what is the rotation of joint O, brother? Theta O is ml by 11 EI, ml by 11 EI. So some people will say like, sir, this type of problem when the load is acting, right? Ambardatta, hi, good morning, brother. This type of problem, everybody will say me like, sir, to find out rotation at a point or to find out displacement at a point. Generally, you had already mentioned like. You had already mentioned like maybe unit load method or maybe Castigliano's theorem. Using that one we can do, yes, you can do the using that one also, but definitely by looking at this one, if you do integral capital mx small mx dx, you need to do 1 2 3 4 4 times capital mx, 4 times small mx, like that you need to do, and you need to substitute. But when the loading, if they are expecting rotation of a rigid joint at a point, so try and when the load is exactly acting at that joint, in such case instead of that unit load method or Castigliano's theorem, directly by using the concept of stiffness of the rigid joint, we are able to work out the rotation of that rigid joint, right? In this way we are able to work out it very easily. I mean, in these types of problems, what is the note I can say is, So I just want to write a note for you. Maybe some people will get confused, like note to find rotation of rigid joint in a framed structure with loading directly on rigid joint. Better use the concept of stiffness of rigid joint. Better use the concept of absolute stiffness of rigid joint. Using that one, you can use rather than unit load method. Or Castiglion's theorem 1, anything. Right, brother? Okay. So can I move to the next slide? I mean, can I talk the another definition? Some people will say like, sir, there is another definition is there. The another definition is carryover moment. So if you please allow me for 1 minute, I will be back in a minute. Is that okay? So please allow me. I will be back in a minute. Please excuse me for that. Hi, bros. Right. Sorry about that small interruption. Okay. Let me start again. Okay. Right. Right. Coming to the next definition. The next definition is carryover moment. So everybody will also ask me, sir, what is this carryover moment? Right. Uh, I can say, what is this carryover moment? The basic definition of this carryover moment is when a moment m is applied at the near end, then the moment that is generated at the far end is called carryover moment. When I just want to write the definition. When a moment m is applied at the near end to have unit rotation at near end, the moment that is developed at the far end, the moment developed at the far end is called carryover moment. People, instead of writing carryover moment, we can write COM, carryover moment, in this way, right? Okay. Now after this one, so I hope you know this is near end and this is far end, and the far end is clearly fixed. The moment that is applied at the near end to produce unit rotation is 4ei by L. 4ei by L. Now what is the moment that is developed at the far end? The moment that is developed at the far end is definitely half of this moment. So I can say I can say this is called as, maybe this is far end, na? The moment that is developed at the far end. This is nothing but carryover moment. So coming to case 1, I can say for far end is fixed, and for far end is fixed, in such case that carryover moment is, if this is m, the direction of the carryover moment at the far end is always in the same direction of the applied moment. How the direction of the applied moment at the near end is, to produce unit rotation, the direction of applied moment, so let me write, the direction of applied moment at the near end is clockwise direction. So the direction of moment applied, the direction of moment that is developed at the far end is half of this moment, and it is also in the same direction, which is clockwise, which is directly we can write as m by 2. Carryover moment is m by 2. So when it is, what is m value is already 4 ei by l, and it is m by 2 in the sense which is 2 ei by l. Now everybody will also ask us, sir, okay, this is for far end is fixed, now you tell me the carryover moment when far end is hinged. When case 2, when the far end is hinged, I mean this is near end, this is near end, this is far end. When the far end is actually hinged, this is hinged or roller support, I can say. So how much amount of moment is required to provide unit rotation at the near end? That is nothing but absolute stiffness. So but what is the moment that is generated at the far end? This moment is m. If this end is a hinged end or roller end, at the hinged end and roller end, it won't resist any sort of moment, because it allows rotation freely, right? So that's the reason why when the far end is hinged, the moment that is generated at the far end is obviously or absolutely it is zero, right? Because this is far end is hinged. At hinged, I hope you know what is the property of hinge. Hinge, at a hinge, it allows rotation, and their bending moment is zero, because it won't restrain any sort of rotation, right? So the far end carryover moment here in this case, when the far end is hinged, is zero, right? So if you please excuse me, can I move to the next slide, right? So I had mentioned the definition of carryover moment. So what is the definition of carryover factor, brother? How I can say about carryover factor definition, right? So carryover factor, so how I could define this carryover factor, brother? What is the definition of carryover factor? The definition of, excuse me, Palpayama. What is the definition of carryover factor, bro? The definition of carryover factor. So coming to the definition of carryover factor, we can directly mention it as, it is the ratio. I hope you can say it is divided by, na? Okay, one second. Let me. It is the ratio between moment induced at far end. This is not far. This is far end. So type. Sorry. Moment induced at far end by moment applied at near end. So moment induced at far end, it is nothing but carryover moment by moment induced at far end is carryover moment of that member divided by moment applied at the near end, which is nothing but absolute stiffness of the member, right? So this is what we can indirectly write, right? Carryover factor. So coming to carryover factor, uh, coming to carryover factor in case of far end is fixed. In the case of far end is fixed, I hope you had already seen, this is, this is near end, this is far end, this is far end. When far end is fixed, okay, when far end is fixed, what is the carryover factor? Here the moment that you need to apply, that moment applied is 4 ei by l, right? At the far end, here the moment developed is m by 2, which is equal to 2 ei by l, which is nothing but carryover moment. The value of that carryover moment is 2 ei by l, right? The moment that is applied at the near end to produce unit rotation, which is the moment applied at the near end, the moment applied at the near end is 4 ei by l. So you can definitely get this ratio is half, and the far end is fixed. So far end is fixed. When the far end is hinged, what is the carryover factor? So maybe I can say the second one is when the far end is hinged. When the far end is hinged, what is the carryover factor, brother? The carryover factor is moment induced at the far end. So what is the moment that is induced at the far end? This is far end. This is far end. This is near end. Moment induced at the far end. So what is the moment in the moment that is applied at the near end to produce unit rotation when the far end is hinged is 3a by L, which is called as absolute stiffness of the member. Far end it is a hinge na, so the moment that is induced at the far end is 0. So I can write 0 by this 3a by L, which is 0 directly. This is how we can work out carryover factor also, right? Okay, so I'm directly going for a question. I'm expecting answer from you guys. Okay, Ved Chintu, Vasant Sai, Anil Madriki, Shebin Sailuddin. Okay, so this is the question. Find the carryover moment for the beam shown below. But this beam, if you see this beam, the length of this AC is L and the length of CB is also L, and there is an internal hinge is there. So you should understand directly, you cannot directly, if this is M is the applied at the near end, this may be, or this may be the near end. What is the moment that is developed at the far end, right? I'm expecting answer from you guys. But when there is no this, when there is no in, this is an internal moment hinge. Internal moment hinge. When there is an internal moment hinge is in this way, generally you cannot directly, when this is M, at this far end you cannot write M by 2 because far end is fixed, but in between near end and far end there is an internal moment hinge, so directly you cannot write M by 2. And coming to degree of static inertia of the structure, degree of static inertia of the structure is 0, right? External static inertia is 1, and internal static inertia is 0, number of releases are 1, so 1 plus 0 minus 1, it is 0, right? Degree of static inertia is 0. Now when I apply moment M at the near end, what is the moment that is developed at the far end, which we people call it as MB. MB is how much? So they are expecting carryover moment means MB. So can you work out what is that moment at B, right? What is that value? If this is M, so I hope this is a determinate structure na. I hope you can directly take the free body diagram of this is the determinate structure. By using equilibrium equations alone you are able to work out that moment MB, which is called as carryover moment, right? So maybe if I take the free body diagram of AC, this is A, this is C, right? At A there is a moment called clockwise M. This is the moment that is applied at the near end, right? Now this is C na, so maybe I can say this is the direction of BC. This is the free body diagram of AC, and at point C, because there is an internal hinge na, the moment is 0, bending moment is 0. Similarly I want to take the free body diagram of CB member. For at point C, the direction of reaction VC at point C is vertically upwards. What is the direction of reaction VC at point C, which is vertically downwards, which is VC, right? VC, and it is fixed at this end. Okay, and it is fixed at this end, and this is C and this is B. Now you tell me, when you are able to, this is length L, this is also length L, what is this moment MB? How you can write this moment MB from the free body diagram of CB? It is VC into L, right? Just the answer is VC into L. If you are able to work out the value of VC, the problem is over na. Now everybody will think like how to work out VC. This is a determinate structure, so simply the common sense says like take the free body diagram of AC and work out this VC. How to work out this VC from free body diagram of AC? So I can write by considering free body diagram of AC. If I apply sigma m about point A, this is clockwise is m, and about this point A, this is VA. Moment of VA will be 0, it is m, and about this point A, this VC is trying to rotate anti-clockwise, minus VC into distance is L. So that the value of this VC is m by L, right? So coming to this MB, which we people call it as carryover moment, right? MB, M suffix B, which is carryover moment, which is VC into L, which is M by L into L. So directly you can write that the direction of this moment is also clear. It is in this clockwise direction only, and the value of M. So the carryover moment. So what is the answer of carryover moment here? Carryover moment is M, I can write. And if you want to work out carryover factor, what is carryover factor of AB? Carryover factor of member AB, how I can write? Force induced at carryover moment by force induced at far end by force applied at the near end, or moment induced at the far end by moment applied at the near end. Moment induced at the far end is m, moment applied at the near end is m, and it is a unit. That carryover factor is 1, right? In this way we can work out. Intentionally I had eliminated the options, brother. If I had given options, so many people will say like this is the option, that is the option, but I just want to know how you can work out this correctly. So that's the reason why I had stopped all the options here in this question. Okay, can I move to the next question? Is that okay? Right, can I move to the next question? So there is another question is there. Before I go to this question, I just want to say, I just want to give one more question to you also. Like the question is, a moment M is applied at A. Okay, the carryover factor from A to B. This is how the figure is. And for your convenience, I mean for your understanding, if you understood this one, you are able to work out this question correctly. And this is A and this is B. A moment M is applied at A. They are saying the moment M is applied at A, right? And coming to in this problem, I am giving you options. So in the what are the options? Option A is half, option B is less than half, option C is more than half, option D is 1. So you need to pick the correct option for this one. So you tell me the flexibility of maybe this may be A to C. Flexibility of AC member is 2I. The flexibility of CB is I. In this case, how you can say when the flexibility is constant from A to B, either 2I or I, in such case at the far end it is m by 2. But here at the far end I can clearly say like at the far end the moment of resistance at the far end that is developed is less than m by 2. Why I am saying less than m by 2? Because lesser cross sectional area or lesser moment of inertia is there. When lesser moment of inertia is there, obviously lesser moment of resistance is possible at the far end. I hope this is near end. Everybody knows this is near end, and this is far end. So at the far end, you people tell me the moment that is developed is less than m by 2, right? Because of lesser moment of inertia. So I can say that one, right? Moment of resistance is directly proportional to ei. So based on that one, we are doing this stuff. And from A to B, I can say from A to B, right? Carryover factor is equal to what is the moment induced at the far end? The moment induced at the far end is at B, which is less than m by 2. And what is the moment applied at the near end? The moment that is applied at this near end is clearly it is capital M. So I can write M. So when I do this one, This is definitely carryover factor from A to B is less than half, right? You can pick less than half. B for Boston is the correct option. But in the same problem, maybe I can ask you the next problem. I am asking what is the carryover factor for above problem. Carryover factor from B to A. B to A if a moment M is applied, the moment M is applied at B. Right now the moment M is applied at B, so because of that one, so I hope you can say this is A, this is B, this is A, this is B. This problem I had already worked out. This problem is already done. I just want to give like when the moment M is applied at the near end in a clockwise manner, what is the carryover factor? So here it is I, right? Here it is 2I, right? So at the when the this is near end here right now in this second case, this may be question 2, this may be question 3. In question 3, if you see the moment that is applied M is at B, when the moment applied is at M is at B, what is the moment that is generated at the far end, right? So can you tell me at the I am applying M, this is near end, this is near end, this is far end. For the far end you tell me, for the far end you tell me what is the moment that has got generated. The moment that has got generated is M by 2, people will think, but when the flexural rigidities are same, it will be M by 2. But here when compared to the near end, far end has got higher flexural rigidity or higher moment of inertia, so I can say here it is not M by 2, it can be more than M by 2, so I can simply say like more than M by 2. In such case carryover factor, this may be, what is carryover factor? Moment developed at the far end, which is more than M by 2, moment applied at the near end, which is M. So in such case this is more, carryover factor is more than half. The question is one and same, question 2 and question 3 are one and same, but the carryover factor of question 2 is from A to B, when question 3 carryover factor is from B to A. Because of that question difference, the answer will get vary like anything. Option A it is half, option B it is less than half, option C it is more than half, option D it is 1. In this case option C you need to pick for question 3, right? More than half. This is how you, this type of question, this question 2 was asked in ESE, this question 3 I am asking. Okay, right? So moving to the next topic, next concept. Okay, right? There is a next concept called, which is relative stiffness of a member. What is this relative stiffness of a member? Right, by the time we want to work out some the future coming topic called distribution factor, by the time to work out distribution factor easily, instead of absolute stiffness of a member, there is another terminology called as relative stiffness of a member is actually given. Relative stiffness of a member, how we can mention. So what is relative stiffness of a member? Everybody will ask the definition. Relative stiffness of a member is nothing but it is the ratio between absolute stiffness of the member divided by 4e. I hope you know the constant 4, and I hope you know the constant Young's modulus e. The absolute stiffness of a member divided by 4e, it is nothing but relative stiffness of a member, right? This, where this relative stiffness of a member is very much useful, this is useful fast, this is very much useful to work out distribution factors of the members fastly, which I am going to teach in the next coming definition. Okay, this is useful to find distribution factors of a member fastly we can use relative stiffness of member instead of absolute stiffness, instead of absolute stiffness of member. Instead of absolute stiffness of member, right? This is the way generally we can write. Okay. Okay, coming to relative stiffness, in this one, now you tell me, if far end is fixed, if far end is fixed, what is the relative stiffness? When far end is fixed, the relative stiffness is absolute stiffness of the member by 4e. What is absolute stiffness of the member when far end is fixed? When it is 4ei by L divided by 4e, you tell me. So this is the relative stiffness of the member. Relative stiffness of member. So here 4 will gets cancelled, E gets cancelled. The answer will be I by L. This I by L's, and this, when far end is fixed, it is I by L. Okay. Now when the far end is hinged, for example in case 2. So in case 2, when far end is hinged, so when far end, this is when far end is hinged, by that time what is the relative stiffness of the member? What is the relative stiffness of the member when far end is hinged? The same basic definition. Relative stiffness is equal to absolute stiffness of the member by 4e. What is absolute stiffness of the member when far end is hinged? 3ei by L, absolute stiffness, right? Divided by 4e, I can write. So E will get cancelled. It is 3 by 4 times of I by L, right? So indirectly I can write, it is this relative stiffness for if far end is hinged case is 3 by 4 times of I by L. This is what we can write, right? Now everybody say, sir, what is the actual definition of distribution factor, sir? How we can write the definition of distribution factor? The definitions of distribution factors we can write in two ways. So coming to the definition of distribution factor of a member meeting at a joint is equal to distribution factor of a member meeting at a joint. Distribution factor of member meeting at a joint is equal to k by sigma k. We can write, what is this k and what is this sigma k? So k, I can write this k and sigma k as the relative stiffness of the member by, I can write. So it is equal to k by sigma k. So if you please excuse me, I will write what is k and all this stuff. Maybe I can rub the screen here. Can I rub the screen here, brothers? Right? Ambar Datta, maybe Anil Madriki, Vasant Sai, Ved Chinu, Vandana Simran are the persons who are on the online. Can I rub the screen? Right? I just want to define what is this distribution factor definition. Right? So erasing all the ink on the screen. So maybe I can say how I can write a distribution factor of a member meeting at a joint, which is equal to, what is k, which is distribution factor of a member is equal to k of that member by sum of the stiffness of all the members meeting at that joint. So how I can write that stiffness of the member? Stiffness, there are two stiffnesses are there. One is absolute stiffness, second one is relative stiffness. So I just want to say it is absolute stiffness of the member by, one definition is absolute stiffness of member by sum of absolute stiffness of all the members meeting at the joint. Sum of all the absolute stiffnesses of members meeting at the joint. This is one definition. if you use absolute stiffness. Some people will come and say, sir, we are not interested to take the absolute stiffness, we are interested to use the relative stiffness, sir. Instead of absolute stiffness, we are interested to use relative stiffness. What is distribution factor of a member? Relative stiffness of the member divided by, if I use relative stiffness, even in the bottom also I should use relative stiffness. Relative stiffness of member by either this one and this one will yield the same result. So but please make sure, like when you are using absolute stiffness on the numerator, even on the bottom also absolute stiffness should be there. When you are using on the numerator relative stiffness, even on the bottom also relative stiffness should be there. Relative stiffness of the member by sum of the relative stiffness of all the members meeting at joint. This is how we can write. डील सील सर हिंदी में प्लीज. डील सी विल डेफिनेटली ब्रदर, जहाँ पे आपको नुकसान होता है उतना तक हिंदी में बता दीजिए, उतना तक मैं हिंदी में जरूर बोल दूंगा भाई. ओके, डेफिनेटली आई विल टीच आल्सो इन हिंदी आल्सो. बट जहाँ पे आपको नुकसान होता है, जहाँ पे अंग्रेजी समझ में नहीं आता है, वहाँ तक आप पूछ लीजिए, बिकॉज माई मदर टंग इज नॉट हिंदी. मुझे तो हिंदी तो आता है भाई, तो डोंट वरी, आप हिंदी में पूछ सकते हो कहाँ से क्या चाहिए, राइट. डिस्ट्रीब्यूशन फैक्टर ऑफ ए मेंबर मीटिंग एट ए जॉइंट इन. ओके, so let me first work out, this is either you can आप ये भी यूज कर सकते हो और ये आप ये भी यूज कर सकते हो. So within these two you can use any of these two. Within these two definitions you can use anything to find out distribution factor, right. So this is the first question, brother, for you. Like, so calculate the distribution factor at B, C, D. So I need to work out. So calculate the distribution factor at B, C, and at D. So distribution factor at joint B. How many number of members are there? कितना members है at joint B पे? BA is one member, and at joint B, BC is another member. So distribution factor of BC निकालनी है, डिस्ट्रीब्यूशन फैक्टर ऑफ BA निकालनी है एट B मीन्स. व्हाट इज डिस्ट्रीब्यूशन फैक्टर एट C मीन्स? डिस्ट्रीब्यूशन एट C के पास कितने मेंबर्स है? CB is one member and CD is another member. It is distribution factor of CB and distribution factor of CD, right. And similarly at joint D, these are the answers directly I had given to you, but I need to derive this. How I got this half 4/7, maybe these are the answers directly, but I need to teach you how I had derived this. Okay, right, yes. So one second. So distribution factor of at D, how many members are there? D के पास DC member है, DE member है. So the distribution factor of DC is how much? The distribution factor of DE is how much? Right? Yes. DLC will definitely. Right. Now, can you people tell me what is the distribution factor of? Before you take in this way, you should think like these are the answers. Some people will say like, okay. You can think at G, at B it's a roller, at C at roller, at D is also roller, but roller supports at B and C are interior rollers. इसकी वजह से क्या होता है? इसकी वजह से बेंडिंग मोमेंट at B and C will come. So because of which bending moments at B and C will occur. So because of which what we can say, I can consider B and C as rigid ones, or consider B and C as fixed ones. So consider B and C joints as fixed ones. Okay, please understand. At B it's a roller is there, C is roller there, but because of that rollers, definitely some moment will be there. If you want to see the bending moment diagram qualitatively, maybe this is how the bending moment diagram qualitatively will be there. This is how the qualitative bending moment diagram will be there. This is how the qualitative bending moment diagram, if it is completely loaded with UDL in this way, right? So okay, shall I work out the distribution factor of BC? Shall I work out distribution factor of BA and BC, right? So at B, the answer given by Dale Civil is wrong, because Dale Civil thought कैसे सोचा Dale Civil भाई, आप B को सोचा रोलर, C को सोचा रोलर, but this is actually roller, बट उसकी रोलर की वजह से यहाँ पे क्या आ रहा है, दिस इज अ रिजिड सपोर्ट एट बी एंड एट सी, इसकी वजह से यहाँ पे मोमेंट आ रही है, राइट? सो आई कैन राइट हियर डिस्ट्रीब्यूशन फैक्टर of member BA. How I can write distribution of factor of member BA? Stiffness of member BA, maybe absolute stiffness or maybe relative stiffness of member BA. So yet for distribution factor for joint B, how many members are there? Distribution factor of member BA is stiffness of member BA by sum of the stiffness of all the members meeting at joint B, that is stiffness of member BA plus stiffness of member BC. In this way we can write. Okay, so what is stiffness of member BA? I just want to use the relative stiffness. Deal civil, my relative stiffness use कर रहा हूँ. Is that okay? So relative stiffness, B is near and A is far end. For BA, B is near and A is far end. For member BA, A far end is fixed. For far end is fixed, it is I by L. So KBA, which is I by L. KBC, B is okay. At far end C, if C is also fixed, because I already mentioned, consider B and C joints as fixed ones, because bending moments are occurring at B and C, you need to consider that as fixed ends, right? So in such case it is fixed end na, so I can write I by L. So I hope कहाँ पे deal civil brother has made a mistake, कहाँ पे आप mistake किया, आपको मिल गया शायद. So it is की वजह से यहाँ से half 1/2 is the answer, right? So what is the distribution factor for member BC? Distribution factor for member BC is relative stiffness of member BC by the sum of the relative stiffness of all the members meeting at the joint B, which is stiffness of member BA at B. BA is one member and BC is another member, right? So KBA plus KBC, right? In this way we can work. What is that KBC? B is near and C is far end. Far end is at C it is rigid or fixed, so I can say I by L, I can write. And KBA, and what is KBA for? This is near end. Far end is fixed, and far end is fixed, it is I by L. For BC, B is near end, C is far end. At C, when the far end is rigid or fixed, in such case it is I by L, which is half. What you understood here? So sum of the distribution factors of all the members meeting at a joint is 1. Distribution at B, at joint B, how many members are there at joint B? At joint B, BA is one member, and at joint B, BC is another member. I can say distribution factor of BA is half and distribution factor of BC is also half, right? So from this one, what is the conclusion? Generally you can write, brother. So can I rub the screen? What is the conclusion that we can write? Distribution factor of sum of the distribution factors of all the members meeting at a joint is 1, right? That is the inference that I can write. Okay, maybe I can rub the screen here. Inference is, notice, sum of distribution factors of all members meeting at a joint is equal to 1. So that is distribution factor of member BA at joint B. Only two members are there. Distribution factor of member BA plus distribution factor of member BC is how much, brother? 1. So when this is half, already this must and should be half. So similarly at joint C, how many number of members are there? Distribution factor of CB at joint C, CB is one member. I hope you can see. At joint C, CB is one member, and at joint C, CD is another member, right? So like that we can write distribution factor of CB plus distribution factor of CD. Directly it is equal to 1, right? So when I work out distribution factor of one member here in this present case, I can work out distribution factor of another member at the same joint, right? So can I work out distribution factor of member CB, right? Can I do that, right? So wait for a minute. Let me drink some pail of water, brother. Let me drink some pail of water. Thank you, brother, for giving time. Yeah. Okay. Distribution factor of member CB. How you can do this distribution factor of this member CB? I can say relative stiffness of member CB. C is near end right now, and B is far end right now for CB. Far end is at this far end it is fixed. You can treat it as fixed. It says fixed because bending moment rigid or fixed, right? In that case, when far end is fixed, I can write I by L. What is moment of inertia of CB? It is I. L is L by I by L divided by distribution factor of CB divided by distribution factor of CB, which is I by L. What is distribution factor of CD? Because sum of the stiffness of all the members meeting at joint C, right, which is CB and CD. For CD at D, it's a roller. It's an exterior roller. When it is an exterior roller, far end is taken as hinged. So in such case, I can write as 3 by 4 times of I by L. So when you do this, definitely you will end up with this answer of 4 by 7. So that's the reason why distribution factor of CB is 4 by 7 we can write. Right. So after this one, how to work out the distribution factor of CB is 4 by 7. Similarly, how to work out distribution factor of CD? Distribution factor of CD. How we can do that one? So I hope you know from this equation where distribution factor of CD we can write as stiffness of member CD by sum of the stiffness of all the members meeting at joint. See, we can write a K CB plus KCD. If you write in this way, for CD it is 3 by 4 times of I by L, because the far end is roller, divided by KCB 3 by 4 times of I by L. For CD, from C is the near end, from CB, C is the near end, B is the far end. For far end it is a fixed one. In such case I can write I by L. In this case, definitely you are about to get this answer as 3 by 7. Either from the fundamental you can work out this distribution factor of CD, or from this inference also you can work out this distribution factor of CD. Is that okay? Right? Right. So moving to the next one. I mean distribution factor of DC and distribution factor of D. Right? So can I rub the screen? Distribution factor of DC. So how you can work out distribute D is the near end right now, and C is far end. When D is the near end, okay, I can write stiffness of member DC by sum of the stiffness of all the members meeting at joint D, which is KDC plus KDE, right? Stiffness of member DC, this is near end, far end is fixed. For DC member, D is near end, C is far end is fixed, right? So in such case I can write I by L. For KDC, I by L. What is KD? D is near end and this is far end. Far end is already a free end. When far end is a free end, absolute stiffness of the member is 0. 0 by 4E will always be 0, right? So in this case this will be directly 1, right? And distribution factor of member DC is 1. What is the distribution factor of member D? I hope if you can see at joint D, there are only two members are there. So from the concept of sum of the distribution factors of all the members meeting at a joint, distribution factor of DC plus distribution factor of DE, it is 1. When this is already 1, what is the distribution factor of DE? It must and should be 0. So from that one we can directly write distribution factor of DE is directly 0. These are the answers directly we had mentioned here, right? If you are able to work out this question, I hope like you can work out any type of problem to work out the any type for any type of problem for any member, you are able to work out the distribution factor, right? So can I move to the next slide, maybe next question? Right, right. So calculate the rotation of this rigid joint. The question is, for this frame shown below, calculate the rotation of the rigid joint. Can you work out the rotation of the rigid joint? Rigid joint O. They are expecting theta O. Theta O is the question. So at joint O, there is a physically a moment is applied, and there is no no other loads are acting on other members. Okay, physically a moment M is applied. I hope you know from the fundamentals of stiffness of the joint. Moment applied on the joint is equal to sum of absolute stiffness of the joint uh, O multiplied by rotation of that joint O, and this is the moment applied at the joint. Okay, so moment applied at the joint O is M, and can you work out sigma KO? What is sigma KO stands for? Sum of absolute stiffness of joint O. Sum of absolute stiffness of all members meeting at joint O. Meeting at joint O. How you can do that one? Sum of absolute stiffness of all members meeting at joint O. So maybe this is O, this is A, this is B, this is C, this is D. So I can say absolute stiffness of OA plus absolute stiffness of OB plus absolute stiffness of OC plus absolute stiffness of OD. I just want to mention here like the flexural rigidity of OA is EI. For this one is also EI. For this member it is also EI. For this member is also it is EI. So absolute this O is near end and A is far end. A is far end. This is far end. This is far end. This is far end. And when there are far ends are there, in such case what we can do, and when far end is fixed, I hope you can say every far end is fixed. In such case absolute stiffness is 4 EI by L. The length of this member is 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 one and same L. So in such case 4 EI by L, here 4 EI by L plus 4 EI by L plus 4 EI by L, so which is 16 EI by L. So in the moment that is applied on joint O is M, that was clearly given. So MO is M, and stiffness of the joint O, it is 16 EI by L. And what is the rotation of that O? Rotation of that O you need to work out. How to work out that rotation of that joint O, which is ML by 16 EI. We can do in this way. ML by 16 EI. This is how we can work out rotation of a rigid joint when the load or moment is actually acting on the joint. No other loads are acting. In such case, we can work out that rotation of the joint O in this way. Okay. Can I move to the next question? Moving to the, before I do this, I just want to rub the screen here. This is the note I want to mention. The note is sum of the absolute stiffness of all the members meeting at sum of the stiffnesses of all the members meeting at a joint is nothing but rotational stiffness of the joint. So how there is another definition is there, which is nothing but rotational stiffness. Rotational stiffness of joint. This rotational stiffness of the joint is sum of the absolute stiffness of all the members meeting at joint. Oh, meeting at a rigid joint. That is nothing but rotational stiffness. So this we had already done, right? Which is right? Yes, we had already done this. So please subscribe to our channel, brother. Right. So if you see this, all this, maybe O, A, B, C, D, that sum of the rotational stiffness of all the members is KOA plus KOB plus KOC plus KOD. This we had done, right? Yes. So one second. Moving to the next question, next problem, or whatever that means. One second. Right. This is the question for you. This was given in this is a own question that I had framed. So I am expecting answer from you. I am giving you 2 minutes to you. So I am expecting answer from you, the guys who are in the online. You can try this one. Consider a portal frame. Consider a portal frame shown in figure. E is equal to 2 into 10 to the power of 5, and I is moment of inertia for all the members of the frame. The rotation in degrees up to 1 decimal. So what is the rotation in degrees up to 1 decimal? That is, they are expecting rotation theta q in degrees. They are expecting. First of all, generally we'll work out the rotation at q, theta q. How I can write moment acting on q? Mq is equal to theta q into stiffness of sigma kq, sum of the stiffness of all the members meeting at joint q, right? But here there is no physical moment was applied on this joint q. But if you take this members tq and qr, okay, if you take this members tq and qr, definitely bros, I hope you can see. Definitely you can see. One second. Definitely here QR is one member and TQ is another member. Take the directions of the moments. Take the effect of this loadings on this joint Q and find out the moments from TQ and QR exactly on joint Q, and show that direction and find out using this equation. Generally by looking at this stuff to find out rotation at joint q, people generally use like, sir, I will use unit load method or maybe cast nasty. If you use that one, in every segment 4 segments are there, and it will be very tedious to work out capital mx in 4 segments, so small mx in 4 segments, and working out that integral again for 4 segments. That is a difficult task, right? So the hint, what is the hint that I can give you is, hint is very simple. Mm, uh, uh, Consider the effect of overhang portions on rigid joint q, and you start working out, right? So if I take that, maybe if I take that now, I hope you know, because of these stuff, because of this loading vertically downward kilonewton per meter, the moment in member mqt, this will be clockwise here, right? Because of the force here this is trying to rotate clockwise. The rotational moment, when the resisting moment in member qr here, this is in anti-clockwise direction. It is from the fundamentals of SOM we are showing the directions in the members. And what is this value of, maybe I can write this as m qt, this is m qr. Can you work out mqr and mqt, right? So if you just take the moments, the moment at q is equal to mqr and mqt, definitely, right? So Can you do this MQT? Right. So coming to workout with MQT, I can write MQT. It is this is triangular stuff. How I can write half into base is 4 meter into height is 20. From the apex it is almost from this apex this distance, this is total force. The force into distance, it is 2/3 of h. So this is MQT we can write. Right. Some people this is which we can call this as 106.667 kilonewton meter. Similarly, what is MQR? MQR. This is 250 into distance is 3. So 250 into 3 it is 750 kilonewton meter. So if I want to take the moment at Q, so what is the moment at Q? This is MQT is clockwise. This is MQR is anti-clockwise. What is the net moment at Q? If I remove these ones generally, which is the combination of MQT and MQR, which is if I take if I take, this is how I can take this. This is how I can take. If I take here on joint, if I take at Q, this is MQT is clockwise here na. On this one it is, and on this member QP it is anti-clockwise in nature. So I can say this is anti-clockwise is 106. Here it is anti-clockwise 106 and 66. Here on this one it is clockwise 750. So here the net moment acting on this joint Q is clockwise 643. So 643.33 is the clockwise moment, and here you can pick it is fixed here, and at P also it is P. So there is a clockwise moment of 643.33 is acting on joint Q, which is it is 750 minus 106.667, which is and definitely it is equal to 643.33 kilonewton meter. Now if you want to work out rotation at Q, MQ is over. So MQ is this much we got kilonewton meter. And how to work out sigma KQ? If you are able to work out sigma KQ, the problem is over na. So how to work out sigma KQ? Can I rub the screen? Can I rub the screen here, bros? Right. So maybe I may use the next slide. Is that okay? Moment of inertia of each and every member is 8 into 10 to the power of 8. Right. So this is how the frame is. This is P. This may be S. At this joint Q, if I had this is the idealized structure. At joint Q there is a clockwise moment. Here it is 643.33. The effect of loading on the members QR and QT I had taken on joint. Take the effects of the members on QR and QT on the joint Q. I had done that one, right? And to work out sigma KQ, how to work out that sigma KQ? Sigma KQ, here only two members are there. Or I can say stiffness of member QP plus stiffness of member QS, and this length is this length is 5 meter. It seems they had given, and this length is also 5 meter. There are only two members right now in the idealized structure, which is 4 EI by L, 4 EI by L. So 4 into EI by 5. This is 4 into far end. Q is near end, I can say. Q is near end. This is far end. This is far end. And the far ends are fixed. I can say 4 EI by L. So I can write 4 EI by 5. So directly I can write 8 EI by 5. What is 8 is okay. What is Young's modulus, which is 2 into 10 to the power of 5 Newton per millimeter square into I. What is Young's modulus? Moment of inertia is 8 into 10 to the power of 8 millimeter power 4 divided by, I should write this as 5000 also. I should write this Newton per millimeter square. this is divided by 5 na, so I can write divided by 5 is in terms of meters. I need to write 5000. So some value you will get. This is what is sigma kq. This is what is sigma kq. If you work out, I hope you know what is mq. Mq is equal to sigma kq into theta q. If you do this one, what is the value of this mq? Moment at q, which is 643.33. 643.33 kilonewton meter. I can write into 10 to the power of 6, which is equal to sigma kq. This is known, okay, into sigma kq into theta q we can write. If you work out from this one, definitely the value of theta q, it is 2.513 into 10 to the power of minus 6 radian. Okay, this is in this way we can work out, right? So they are expecting this question, this rotation in degrees up to 1 decimal. 1 second, maybe I can easily work out. This is 8 into 2 into 10 raise 5 into 8 into 10 raise 8 by 5000. This value of kq I can write as 2.56 into 10 to the power of 11. So maybe I can write 643.33 into 10 raise 6 divided by 2.56 into 10 raise 11. The answer is 2.51 into 10 to the power of theta 10 to the power of minus 3. This is minus 3 radian. And after this one, I hope you know 1 degree is pi by 180 radian. But how many radians I got here? 2.513 into 10 to the power of minus 3 radian. Then how many degrees? Can't you work out this one? So if you do this one, this value into 1, this value into 180 divided by pi. So the answer for theta q in degrees is 0.1439 degrees. You can write. This is what you can write. Finally, in this option here, it is 0.1439 up to 1 decimal na, so this is 0.14. So you can write 0.1 degree is the correct option. I can say, forget about degree, just you need to type in the blank, in the numerical answer type, you need to write, you need to type 0.1. If you type 0.1, the answer is correct. Okay, right. So moving to the next question. One second. Dear brother, this question is framed by me. Okay, this is not there in anywhere. This question is framed by me, right? Okay, moving to the next question, bros. This is the next question. I hope you are able to see. This question is also framed by me. Okay, can you see this question? Just say how many of you people, if you are in online, just say, are you able to see this question? I am giving you 1 minute to you. Can you work out this question? This is a multiple choice question, MCQ question. Can you work out this? Find moment at fixed end A. So when this is an indeterminate structure, how to find out moment at A that they are expecting? Generally, looking at this one, they think like it's an indeterminate structure. Yes, this is an indeterminate structure. But when you work out the moment at O, because of the supplied loads, especially in case of overhangs, when only the load is on the overhang, try to consider the effect of this overhanged load on the joint, and based on carryover moments, you are able to work out, right? So can you work out, can you idealize the structure? The hint that I can give you is structure. This is p into distance is l. This is how the force in, this is how is m o o b m o b. This is how it is m o b. So can you show the same moment on this joint o? Yes, the joint o, the same moment on joint o can be reversed and can be shown. So can I show that? This is how, right? This is how, the direction of moment at joint O from member OC. The direction is reverse. This is on joint O. This is P into L. This is EI. Length is L. This is EI. The length is L. This is EI. The length is L. Right. So after you do in this way, this is A. This is O. This is C. This is D. Now can you work out what is the moment at joint O? I hope you can say when a moment m is applied at a, I just want to convey one more thing. What is the common, what is the physical meaning of distribution factor? When a moment m is applied at a joint, the moment is the moment is shared in the associated members based on the distribution factors. I just want to write that. When a moment m is applied at the rigid joint, the moment m is applied at the rigid joint, then what is going to happen? Then when a moment m is applied at the rigid joint, then associated members will take the moments, take the moment applied at joint based on distribution factors, of the member. So when I apply a moment m, which is called as PL at joint O, what is nothing but member O, MOA? What is moment in MOA? The moment MOA is equal to distribution factor of member OA into applied moment at joint O, which is PL. Moment MOD, which is nothing but distribution factor of member OD into the applied moment acting at that joint O, rigid joint, which is PL. MOC, which is equal to distribution factor of member OC multiplied by, and distribution factor of member OC multiplied by the moment acting under joint O, which is PL. This is the way how we can do, right? Now coming to this, now can you work out? I just want, I mean, as the question was asked only to find out the moment at fixed and A. So as they are expecting moment at fixed and A, I need to take the free body diagram of member OA only, right? So if I take the free body diagram of member OA, O and A, O is near end where the moment is applied, B, A is far end. What is the moment at point O? It is mem OA. What is the moment that is developed at the far end when the far end is a fixed end? When the far end is a fixed end, the moment that is generated at the far end is half of the applied moment at the near end. So which is MAO is equal to MOA by 2. If you are able to work out MOA, the problem is over, right? Isn't it or not? From the free body diagram, I am showing in the free body diagram of member OA only the directions of moments. Of course, in addition to this one, directions of shear forces will also come, right? This is the directions of shear forces. Okay, now you people tell me, okay, right? Now you people tell me, what is the value, how to work out MOA? The value of MOA we can directly work out from the distribution factor of OA into PL. So how to work out the distribution factor, right? So maybe I am working out distribution factor of member OA, right? So distribution factor of member OA, how we can deal this one, distribution factor of member OA. uh, I can simply distribution factor of member OA, it is equal to stiffness of member OA by sum of the stiffness of all the members meeting at joint. So sum of the stiffness of all the members meeting at joint. So I can say KOC, KOD, KOA, KOA plus KOC plus KOD. Right? Some people will also ask us, what about KOB? In the idealized structure, there is no B element is there. Na? You can forget in this idealized structure, in this shortened structure, right? So I can write. I hope you can see. mm, so this is near end. This is near end. Whereas this is far end. This is far end. This is far end. Two far ends are fixed, one far end is hinged, right? So I can say stiffness of member OA. How I can write? I can write I by L. Stiffness of member OA. Stiffness of absolute stiffness, relative stiffness of member OA, IL. Stiffness of member OC. What is stiffness of member OC? See, for OC member, if R and D is hinged, na, so I can write 3 by 4 times of I by L. I can write 3 by 4 times of I by L. So stiffness of member, absolute relative stiffness of member OD. Far end is fixed na, so I can write I by L. So in this case, how we can write this one, man? We can directly write this as 4 by 11 if you do. Now distribution factor. What is the distribution factor? What is the MOA? MOA is equal to distribution factor of member OA, which is 4 by 11 times of applied load PL. What is the answer of MAO, which is the what is the moment at fixed and A, which is called as MAO. What is MAO? Moment at point A in member AO. It is what is nothing but MAO, which is called as moment at point A, which is half of this moment na, MOA by 2 that we got, which is 2 by 11 times of PL, right? So I can pick this option B for Boston is the correct one. Is that okay? Now moving to the next problem, right? I can say like please subscribe to our channel, Let's Crack GATE and ESE. When you subscribe to this channel, Let's Crack GATE and ESE, so many notifications will also come to you, brother, right? Right, before I start the moment distribution procedure na, I just want to say one thing. I need to teach you the fixed end moments. After I teach you the fixed end moments for standard cases, I will teach you the procedure of moment distribution. After the moment distribution procedure is over, we will work out all the objective questions. Is that okay? Right, so please allow me, I'll be back in a minute. Okay, I'll be back in a minute, please. Right, okay, shall we shall we start? Wait for a minute. Okay. Okay, bros. Let me start giving you. Let me start giving the standard case of initial moments for fixed beams. For this moment distribution method, you require even the fixed end moments for standard cases. So let me give the fixed end for standard cases. The sign convention that I am going to use is clockwise moments are positive and anti-clockwise moments are negative. So clockwise is positive and anti-clockwise is negative. This is the sign convention that I will follow in the procedure of moment distribution method. In the procedure of moment distribution method. The procedure of moment distribution method, I use this sign convention. Don't think, some people will also ask me like, sir, sagging is positive, hugging is negative. That is the sign convention. Generally, I use by the time I draw the bending moment diagram, I use that sign convention. This is a sign convention for the procedure of moment distribution method. Please understand the difference between sagging, hugging, clockwise and anti-clockwise. Sign convention is this for this procedure of moment distribution method. So okay, so when a load, I hope you, when a load, when it's a fixed beam, when it is a fixed, I hope you can see, when it is a fixed beam is there with a point load at the midspan. So by that time, what is the value, what is the value of this fixed moments? Generally, MFAB. What is MFAB? MF stands for fixed end moment. Fixed end moment at point A, at point A in member AB. Fixed end moment at point A in member AB is nothing but MFAB. What is MFB? MFBA? This is BA. So what is MFBA? Fixed end moment at point B. At point B in member BA. That is nothing but MFBA. You can even work out, or you can even derive this one also, but if you keep on deriving, the time will be over. So that's the reason why I'm directly giving you formulas. uh, Generally, when the load is W is applied, the moments that are developed are hogging, which will try to lift the beam up. So here the direction of moment is anti-clockwise, here the direction of moment here it is clockwise. As it is an anti-clockwise moment is there at MFAB, I can say MFAB is minus, and it is the load, W is the applied load, and L is the length of the member, minus WL by 8 is the answer when the load is exactly acting at the midpoint. And MFBA, what is fixed end moment in member BA? And it is clockwise. I hope clearly you are able to see. This is clockwise, so it is plus, which is plus WL by 8. Right, some people will say like, sir, how you got these answers? These answers generally we can directly get from consistent deformation method. The rotation at A will be 0 and rotation at B is 0. So because of this applied load, maybe I can write this one as a combination of this one, which is W, because of which one this rotation is downwards, maybe theta 1. So plus same simple support moments with moments which is M F A B M F B A. So because of which the rotations are upwards, the net rotation here it is theta 2. You can work out from rotations. You already know what rotations are standard cases. When you equate theta 1 is equal to theta 2, definitely you are able to get MFAB and MFBA, and you know MFAB is equal to MFBA for this I can say for this symmetrical for this symmetrical structure, right? So using that concept, node theta 1 is equal to theta 2, which is from consistent deformation method, the net rotation at A or at B is 0, right? using this one, you are able to work out. This is my WL by 8. This is anti-clockwise. This is clockwise. It is plus. As negative, as anti-clockwise direction moment is negative, so I am using minus. As the clockwise moment is positive, I am using plus here. Right. So this is case 1. Coming to case 2. So coming to case 2 is, let us suppose when the load W is not exactly at midspan, it is eccentric. So maybe this is the midspan. So from this, from this end A, it is at a distance of A. From the end, from end B, it is at a distance of B. So I can write, yeah, this is MFBA, right? So this is also MFBA, right? Now in this case, what is this fixed end moment? This fixed end moment, this is anti-clockwise and this is clockwise. I hope clearly you are able to see. This is anti-clockwise and this is clockwise. Anti-clockwise moment is minus, so I write MFAB is minus because it is an anti-clockwise moment. Anti-clockwise moments are negative, so minus WAB square, WAB square. So this longer distance square, here the load is towards this point A, load is towards this point A. So in such case, longer distance square, longer distance is B. So A is shorter distance and B is longer distance. So A longer distance square into shorter distance by L square. This is how we can write. And coming to MFBA also, we can write as, at B, here I can say, here at B there may be lesser moment is there, so I need to write the distance square as lesser distance square. Lesser distance square is this much, so I can write this is maybe I can say in this present case, here I can write A is less than B. In such case you can directly write in this way, right? Even for W, I can write W, this is distance is B, this distance is A square by L square. So this is clockwise, so you can treat it as positive. And coming to case 3, when it is completely loaded with UDL, when it is completely loaded with UDL and the UDL intensity is W and the UDL intensity is W, in such case, here it is anti-clockwise moment and here it is clockwise moment. So where here in this case 3, W stands for UDL intensity. W stands for UDL intensity. And when W stands for, when it is UDL intensity, which is WL square by 12, it is WL square by 12. In this case, how you these are anti-clockwise now, so it is minus. This is clockwise, it is positive. So these are the standard for standard equation, standard formulas. Directly we can derive this one also. And coming to the next case, or maybe case 4. In case 4, when the loading is completely downwards, just like the loading is a triangular uniformly varying load, uniformly varying load, UVL, uniformly varying load, UVL. When it is uniformly varying load, now in case of uniformly varying load, the fixed end moment because of uniformly varying load, and the maximum intensity of this uniformly varying load is W per meter. W maybe kilometer per meter or anything. W, I mean it's a uniformly varying load. The maximum intensity is W per meter. So in such case, it is WL square by 12 and it is WL square by 12, where W stands for maximum intensity of uniformly varying load here. And here, just by looking at this loading, you can understand fixed end moment of AB is more, fixed end moment of BA is more, whereas fixed end moment of AB is less because higher load is on the side of B, right? So I can say on MFBA it is WL square by 20. Here it is 20 because higher moment, so denominator should be less. Here it is lesser moment, denominator can be high here, and it is anti-clockwise moment, so minus. Here it is clockwise moment, here it is plus. So that's how you can write. And coming to case 5, coming to case 5, here in this case 5, when a moment M, I hope when a moment M is applied at a distance of A from the left hand side span, at a distance of B from the right hand side span, in such case how to work out that one. In case of, I just want to convey one thing, I just want to, the note that I want to convey is, Initially, especially for this case 5, the directions of the applied moment is in clockwise fashion na? So initially, especially for this case 5 where moment is applied on the member, initially assume the direction of the support moments due to moment or couple is same as that of applied couple. So the applied couple is clockwise. So here also I can say, so here also the direction of these couples, here also direction of these moments are also clockwise in this way, I can say, right? So it is starting stage. So I am taking here, it is positive plus m into b into 2a minus m into b into 2a minus 2a minus b by l square, here you can write. And here for this one it is m into a into 2b minus a by l square, which is mfba. This is how we can get. If you got negative answer in these values, you can understand these directions are in anti-clockwise. Some people will say like, sir, there is a special case, like sometimes when in case of fixed beam, sometimes when the moment is applied exactly at the midspan, when the moment is applied exactly at the midspan, and in this special case where a, this is b, where a is equal to b is equal to l by 2, in such case this direction of these moments are definitely clockwise and the values are magnitudes is m by 4. Values are magnitudes is m by 4. Of course you can keep a is equal to b is equal to l by 2 in this formula. You are going to get that answers, right? Okay, now moving to the another, I mean, there is last one, last special fixed condition when it is uniformly varying, just like in case of two type of triangles are coming, in such case how to do, maybe I can say, this is how the loading is. This intensity is w, and this is acting at a distance of l, I mean total length is l, and it is a symmetrical way. This distance is l by 2 and this distance is l by 2. In this case the directions of these moments are 5 w l square by 96. Here also 5 w l square by 96. This is another the other standard case that I can say. Okay, as the standard cases are already over, so let's move to the procedure of moment distribution. Is that okay? Can I move to the procedure of moment distribution? Right? Can I move to the procedure of moment distribution? I just want to rub the screen before I start the procedure of moment distribution. Okay, I'm erasing. So this is the procedure, right? So step one, I mean step one, step two, step three, step four, 8 steps are there. 8 steps I need to explain. I will explain these 8 steps by taking the help of a small sketch, maybe a small problem. Is that okay? So can I take a small problem to explain all these steps step by step? So maybe I can say I am taking a structure, maybe I can say I am taking a structure here in this way. I am taking a structure in this way. This is a, I am taking an indeterminate structure, indeterminate beam I am taking, A, B and C. This is how I had taken. And this the length of the member AB is 4 meter and the length of member BC is again 3 meter. This is 4 meter comma I, this is 3 meter comma I. And in addition to this one, other to teach you the step number one, intentionally I am providing, this is not directly as a beam, a bracket I am providing at the midspan of AB in this way. On the bracket a load of 40 kilonewton is applied, and this distance is already 0.5 meter, right? And maybe A, B, C, maybe I can write this as D. So what is this everybody can directly analyze if they know this moment distribution method. If you say from A B D A D B B C, generally in this way, you need to convert this structure. This structure is looking awkward. I mean, the structure is not simple to analyze. You need to take the effect of this 40 kilonewton load exactly on point D. This B, this is a bracket one. I mean, this color, this is a bracket. The load is acting on the bracket. The load from the bracket I need to show. I need to show the effect of load from the bracket on the member AB exactly at point D. So how I can do? That is what is idealizing the structure, that is simplifying the structure. So at A, maybe I can say, if this is 40 is here, so at D if I apply, I am showing idealizing the structure means taking the effect of this 40 kilonewton at point D. How I can show? Let me show with the help of two equal and opposite force. This is 40, this is 40, and this is also 40. I hope you are able to see this. These two are, this is 40 and this is 40. These are two are equal and opposite forces with eccentricity of 0.5. Na? So you can easily consider this one as. I hope you know from the fundamentals of your engineering mechanics and from the fundamentals of some two equal and opposite forces. I hope you can see two equal and opposite forces with eccentricity of 0.5 will be converted as a couple. So I can show that couple at point D, right? So I just want to show that couple at point D. This is 40 kilonewton. So removing these two, 40 into 0.5, this is 20 kilonewton meter. Right, 20 kilonewton meter. And at B there is a roller is there, and at B at C also there is a roller is there. I hope when this is 4 meter, this distance is already 2 meter, and this distance is already 2 meter. This distance is 3 meter, right? So this is the actual structure. From the actual structure I had idealized, I had converted that into a simpler form. This is nothing but idealized structure. Maybe I can say this one as directly step 1. Is that okay? Step 1, I can write it as step 1. That is idealize the structure. Simplifying the structure is nothing but idealizing the structure. Simplify a structure. After I simplify the structure, step number 2 is calculate distribution factors at all the joints. So distribution factor at A, distribution factor at joint B, distribution factor at joint C. For all these things I need to work out. At joint A, only one member is there. Na? Distribution factor of member AB is directly I can write as 1. So maybe I can directly take this as 1. And at the joint C also there is only one member, so distribution factor of member CB is directly 1. I am writing distribution factors directly in this brackets, and right now I need to write the distribution factors especially for this member. What is this member? This is for member BA and for member BC. I just want to write the distribution factors of member BA here. This is for member BA, this is for member BC. Now can you tell me how you can evaluate the distribution factor of member BA? Maybe I can say distribution factor of member BA. How you can write stiffness of member BA by sum of the stiffness of all members meeting at joint B, which is BA plus BC. So B is near end and A is far end. When B is near, A is far end is fixed. So I can write I by L. I by L is 4 divided by I by L. I, where B is okay, B is fixed. B at C, C it's a far end. C is far. This is near end. This is C is far end. For far end, it is a roller end, and far end is a roller end and simple supported end. In such case, I can write the stiffness of that member as 3 by 4 times of I by L. I by L length is 3. So in such case, you will get I by L, I by 3. So 3 will get cancelled. So I by 4 divided by I by 4 plus I by 4. So directly we can write 0.5. So that means distribution factor of member BA is obviously 0.5. Similarly, can you work out distribution factor of member BC? I hope you already know a rule. This sum of the distribution factors of all the members meeting at a joint is 1. In such case, what is the distribution factor of member BC? So which is 1 minus distribution factor of member BA, which is 0.5 only. That means I worked out even step 1 and step 2. Step number 3 I need to work out, right? So to work out step number 3, if you please excuse me, can I rub the screen here to work out step number to work out step number 3? Okay, can I rub the screen to work out step number 3? So coming to step number 3, calculate the initial fixed end moments. So I will take the structure as it is. I will take the idealized structure, simplified structure. This is how this is step number 3 I can write. This is 40 kilonewton, right? And this is clockwise, this is 20 kilonewton meter. This is B, this is B, this is C, and from B to C it is uniformly distributed load, and the uniformly distributed load is 20 kilonewton per meter, right? This is how I had taken. This distance is 2 meter, this distance is already 2 meter, this distance is 3 meter, and flexural of this one is A and the flexural of this one is A. What is step number 3? Can you see? Just you need to follow this procedure. If you are able to follow this procedure, you are able to work out that one. After we work out the problems by using this procedure, this moment distribution method, we will work out the same problems shortly without doing the graphical, without using any sort of tabular form. Okay, right. Calculate initial moments assuming a restrained structure. What do you mean by restrained structure? uh, at each and every joint, fix all the displacement. There should not be any displacement at each and every joint. So that means fixing each and every, fixing each and every, they're making displacements as 0 at each and every joint. At A it is already restrained. At B I need to stop all the displacements at B. I need to stop all the displacements at C. So in such case, maybe the structure will become as fixed support. This is step number, this is fixed, and here also it is fixed. Now because of this AB portion, especially if you take for AB, okay, for maybe let me take, especially for member AB, if you take, I had restrained the structure. There are two loads are there, brother. One is by applying with this 40 kilonewton, and second one is, I hope you know, the fixed end moments I can work out in AB by taking the effect of 40 kilonewton load separately and taking the effect of 20 kilonewton load separately, and I need to add, right? Right. So because of this 40, so I hope you know these moments here are anti-clockwise here. These moments are clock. This is anti-clock, and the anti-clock moment is how much, brother? Anti-clock moment is W L by 8, which is W is 40, length is 4 by 8. 4 ones, 4 twos, 2 ones, 2 twos. This is to anti-clockwise 20. This is clockwise 20. This is anti-clockwise 20. And here also these moments here are because of moment M. This moment M is acting at half of the distance. This is 2 meter and this is 2 meter. So distance directly, this is M by 4, which is 20 by 4. 20 by 4, it is 5 kilonewton meter. This is also 20 by 4, M by 4, 20 by 4. This is also 5. So if I add up these two, generally you can understand one is anti-clockwise and another one is clockwise, so the resultant moment here will be in step 3 here. Okay, in step 3 here you can show that. Okay, similarly for BC also I need to work out. For BC, what are the moments for BC? Fixed, I need to work out initially assuming restrained moments, or restrained moments are also called as fixed end moments. Initial fixed end moments, how to work out that one? So I hope you already know, and it is a fixed beam at B and C. Because of this UDL, this end is WL square by 12, this end is WL square by 12, and the value of this WL square by 12 This W is 20, L is 3 square by 12. W L square by 12, this will be definitely it is 15, and it is 15 and this is plus 15. So you had shown the directions, right? Right, isn't it or not? Now if you please excuse me, I will go with the help of a tabular form from step number 4 onwards. So if you please excuse me, I am going for a tabular form. Can I rub the screen? I had completed till step number 3. So from step number 4 onwards, I need to show the help of a tabular form. So to write the tabular form and all the stuff here, I require some space. So I am just rubbing the screen, bro. Okay. I hope when you add up this anti-clockwise 20 and clockwise 5, the resultant at A is anti-clockwise 15. The result here it is clockwise 20 and here it is clockwise 5. So here it is clockwise 25, right? Clockwise 25. Similarly for member BC, fixed end moment in MF BC, it is anti-clockwise 15. So here it is anti-clockwise 15. Fixed end moment fixed end moment at point C in member CB, it is clockwise 15. This is how we can do, right? Okay. Right, so can I rub the screen to show that? Erase all ink on the slide. I am just going for a tabular form, and the tabular form is just like this. Maybe I can show, yes, clearly here. Maybe this is member. Here there is AB member is there. I hope you can see this is how the structure is. This is how the structure is. Right. This is A, B, C. At joint A, how many number of members are there? Maybe here I can create this is joint A. Here I can say joint B. At joint B, how many number of members are there? BA is one member, BC is another member. Similarly, at joint C. At C, how many number of members are there? CB. Right? I just want to write here fixed end moments. Fixed end moments or initial fixed end moments. Initial fixed end moments. It is in member AB it is minus 50, anti-clockwise 15 it is minus 15. In member BA it is clockwise 25, so it is plus 25. In member BC it is anti-clockwise 15, so minus 15. And in member CB it is clockwise 15. The same thing clockwise and anti-clockwise here I mentioned with the help of plus and minus. Clockwise is plus is clockwise and minus is anti-clockwise. I can use this now. So after this initial fixed end moments, right? After this initial fixed end moments, now what you need to do? You need to go through step number 4. What is step number 4? Release or unlock the end moments at simple supports. So at exterior simple supports at the ends, or at exterior simple supports only. At exterior simple supports only, release or unlock the moments. What is the exterior simple support here? So point C. At point C I need to unlock means I need to make the moment at point C in member CB as 0. So how I can do that one? So that means releasing or unlocking the end moments at simple supports at the end, or at interior or at exterior simple supports. I can say balancing, because I am making at exterior simple support moment is 0. But what is the moment that you had got from step number 3? It is plus 15, and I need to make it as 0. How I can make it as 0? So at joint C, if I apply an anti-clockwise moment of minus 15, so clearly if I am applying a moment of at joint C, clearly I am applying a moment of anti-clockwise moment of 15. that total anti-clockwise moment physically I am applying is resisted by member CB only, because there is only one moment, there is only one member is there. So balancing, if I say it is balancing, so it is minus 15 is there. That means physically at C you are applying a moment of minus 15 or anti-clockwise 15. So at a point you are applying, at a rigid joint you are applying, this is the at a rigid joint you are applying a moment called 15, and it is in anti-clockwise, this is near end. So at the far end, this is far end, right? Maybe let me show, this is near end right now, this is far end. At the far end, at the far end, I hope you had already known the concept of carryover moment. At a near end, if you apply a moment m at the near end m, if I apply a moment m at the near end, how much amount of moment is carried over to the far end when the far end is a fixed one? Here at B, it is an interior roller, you can treat it as fixed. When the far end is fixed, how much amount of moment is carried over? I can say simply carryover moment. Carryover moment is possible only to the nearer adjoining far ends. The nearer adjoining far ends are, what is far end of CB? It is BC, right? Far end of CB is BC. So I can say in member BC, a carryover will happen. How much moment will be carried over? The moment that is carried over when the far end is fixed is half of the moment. In such case, what is the answer? It is minus 15 by 2. So I can say minus 15 by 2 is how much, brother? So can I write it as minus 7.5? Yes, that is step number 5. Step number 5 is apply carryover to the nearer adjoining supports. After you unlock the end moments at the at the exterior simple supports, you need to apply carryover to the adjoining nearer adjoining supports. I had made carryover to the nearer adjoining. The nearer adjoining support is only B. There is no other nearer adjoining support other than B, right? So I had done it as minus 0.5. So after this one, and what is step number 6 that was mentioned? In step number 6, they had clearly mentioned like calculate, right? Calculate modified initial fixed end moments. You need to work out the modified initial fixed end moments after the end simple supports are balanced and necessary carryover is made. So after step number 4 and 5, you need to work out modified initial fixed end moments. So I mean modified moments. So can I work out here modified moments? Can I write here modified moments? Modified fixed end moments. Modified fixed end moments. Modified moments. So in member AB it is already minus 15, direct it is minus 15. In member BA it is already plus 25, it is plus 25. In member BC, you are able to see one is minus 15, another one is minus 7.5. That means physically you should understand, when you are applying a moment 15 here at this end, the moment of 15 by 2, the same direction will be carried over to joint B in member BC, which is 15 by 2, which is 7.5. So this 7.5 is the carried over moment. These two moments and these are in clockwise, these two are in anti-clockwise. So minus 15 minus 7.5, which is minus 22.5. Minus 15 minus minus 15. Minus 15 minus 7.5, it is minus 22.5. Here it is plus 15 minus 15, so it has become 0. These are the modified initial moments. After this modified initial moments are there, you need to work out step number 7 and 8. Step number 7 and 8. What is the other name for this moment distribution method? This is also called as equilibrium method. After this carryover is there, after the carryover was done, and as being this an equilibrium method, I can say like balance the, in step number 7, check the balance of internal support moments, because this is an equilibrium method also na. To mention these are the final moments, you should understand like when you add up the interior moments, when you balance the interior support moments to satisfy moment equilibrium equation. So what is the moment equilibrium? What is the moment equilibrium equation at interior support moments? What are the interior supports here? The interior supports are only B. So if you take the joint B free body diagram, brother, if you take joint B free body diagram, this is B. This is called, this is member M. This is at joint B. There are how many number of members are there? BA is one member, BC is another member. This is moment in member BA, MBA. This is moment in member BC. So to satisfy moment equilibrium equation, if you apply sigma m about point B is equal to 0, you will write MBA plus MBC is 0. That's what is check, add up all the moments at the interior joints, so that it is satisfying the moment equilibrium equation or not. Also you need to check. So if you take at joint B, in member BA it is plus 25, in member BC it is minus 22.5. If you add, if you, by adding up these two, are you getting it as 0? No, you are getting that answer as plus 2.5. That means the internal support moments are not balanced. When the internal support moments are not balanced, should understand these moments are not the final moments, should balance the unbalanced internal moment plus 2.5 by applying physically a minus 2.5 moment at B. So the unbalanced moment is the unbalanced moment here, it is by adding up these two, the unbalanced moment is plus 2.5. Will you accept that? Unbalanced moment is plus 2.5. So please excuse me, I will do step number 7 and step number 8 in the next coming slide. I am doing the same thing, step number 7 and step number 8. I will do this balance internal support moment, and if there is not balanced, the unbalanced internal moment is distributed in the ratios of distribution factors and apply carryover. So to deal this seventh step, okay, I just want to deal this seventh step, okay. Maybe here the same stuff I used here. This is minus, I can say this is minus 15, and these are all all these are all modified fixed moments. These are modified moments. After this modified moments, if you work out, if you take these two, maybe this is member member AB, this is member BA, this is member BC, this is member CB, right? So if you add up these two clearly, if you add up these two, it is plus plus 25 minus 22.5. The unbalanced moment at joint B is plus 2.5 is the unbalanced moment, right? So I hope you can see the unbalanced moment right now. Moment, unbalanced interior moment at joint B is plus 2.5. Now when it is plus 2.5, how you could balance that unbalanced moment plus 2.5? Physically, the extra moment at joint B inside at joint B is plus 2.5. To make it, to subside it at joint B, physically I am applying an anti-clockwise moment which is minus 2.5. When I apply an anti-clockwise moment minus 2.5, how much amount of moment is taken care by member BA? How much amount of moment is taken care by member BC when I apply an anti-clockwise moment of 2.5 to balance the interior moments at B? So I can say here this is balancing. When I applied anti-clockwise minus 2.5, when anti-clockwise minus 2.5 means minus 2.5, when I apply minus 2.5 at joint B, out of minus 2.5, how much moment is distributed to member BA, how much moment is distributed to member BC? So the distribution, the distribution, the balancing, after this balancing and distribution, I can write balancing and distribution. This is the balanced, the balancing and distribution in member BA. The moment that is taken care by member BA when I apply anti-clockwise 2.5 is, so MBA, it is equal to distribution factor of member BA into moment applied at joint B, which is 2.5, and it is 2.5 distribution. It is 0.5 into 2.5 and it is minus 1.25. Why it is minus? Because it is an anti-clockwise fashion. So I need to write it as minus 1.25 here and it is minus 1.25 here. That means I had balanced the interior moments, interior support joint moments, and I had maintained equilibrium. After this balancing and distribution is over, so this is the moment that is has got distributed to the associated members. This will be the near end. Now I can say this will be the near end, and this is the near end. Now at the near end, at the near end, in a member, if a moment of 1.25 is applied, if the far end is fixed, how much amount of moment is carried over after balancing? After balancing and distribution of moments, is there any carryover is also possible? You need to do that carryover also. I hope you can see the unbalanced internal moment is distributed in the ratio of distribution factors and apply carryover also. And after distribution I need to apply carryover. What is the carryover from B to C? At C it is a hinged one, na? The carryover moment to C is 0 because it is a hinged one. It won't resist any moment. But at A, in member AB, the carryover is half of this moment. What is half of this minus 1.25? Minus 0.625 I can say, right? So this one I can write it as carryover. This one I can write, this step I can write as carryover. This step number 7 is already over. Even after carryover, you should check, like after doing any sort, after doing carryover, should check like is there any is there any imbalance, is there any imbalance in interior moments has happened or not. After this carryover of this to this side, the internal joint B, interior joint B doesn't attract any sort of extra moment, so that if you add up the internal joint B is satisfying moment equilibrium. There is no disturbance in internal there is no disturbance in internal moment equilibrium equation, right? The internal moment equilibrium equation is satisfying at interior joint B. There is no disturbance is there after carryover also. So by the time, I mean, there is if the internal joints are not satisfying the moment equilibrium equation after I do this carryover, again I need to balance those moments at the interior joints and balance distribution and carryover. Again those steps I need to perform again and again, by fortunately or by God's grace. After this carryover of this 0.625 to this NDA, the internal moments at B like MBA and MBC are not at all changed, right? There is no extra has came. So by the time I can stop this moment distribution, I can stop this iteration procedure, right? So the step number 8 is again carryover balance carryover. The process of balancing can be restricted in a trial where the value of moment where the value of unbalanced moment is where the value of unbalanced moment is less than 10 percentage, is less than zero point 0.1. So that means if you add up MBA plus MBC, its value should be less than 0.1. Then we can practically stop the iteration, right? So these are after this carryover, the again this iteration process is not required by God's grace. So I can say here, clearly, these are the final moments. These are the final moments. So how you will get this final moments, brother? So minus 15, try, these are the modified, to this modified moments add up all the minus 15 minus 0.625. So minus 15 minus 0.625, it is 15.63 or minus 15.625 or 663 you can write. If you add plus 25, I hope clearly you can see. Plus 25 minus 1.25, it is plus 25 minus 1 to 1.25, it is 23.75. Here minus 22.5 minus 1.25 minus 23.75. You add up these two because at B only these two members are there. The moments in these two members, if you are adding up, it is directly equating to 0. So it is satisfying the moment equilibrium condition even after carryover is there, and it is 0 0. So these the moments that we are getting right now are directly the final moments, like that we can mention. Okay, so if you please excuse me, I will be back in a minute after this one. So before I start this stuff, okay, right now after you work out these initial moments, after you work out these moments, you can understand like the moments that we got, the moments that we got right now are final moments, and the indeterminate structure has got converted to determinate stage. When the structure has got converted to determinate stage, and it is up to us, we can start working out the problems, right? So if you please allow me, just after 1 minute we will start working out all the objective questions. Is that okay? Right? So if you can, you give me a minute, a small 1 minute. I'll be back in a minute. I'll be back in a minute. Okay, right, right. Okay, okay, bro. Okay, right. This is the first question that we are going, right? I hope you are able to see this question, right? Can you see this question, right? I'm giving you a minute to you to work out this question. Okay, okay. Let me start working out this question. I hope the magnitude of bending moment at the fixed end. What is the magnitude of bending moment at the fixed end, which is MA, as shown in the figure below. So some people will also ask us, sir, can we do with the help of tabular form? Yes, the first two questions or three questions, till by the time you will understand, I will work out the problems by using tabular form. But after three questions, I will work out in a shorter way by physical understanding in a pictorial way. Okay, so I am taking the structure as it is. This is how the structure is. Okay, at B it's a roller. Let's see. This is how the load is 30 kilonewton, and maybe this is 120 kilonewton. This is 2 meter. This is 2 meter, and again this is 2 meter. This is how the load is applied. Okay. Now you people tell me clearly here, what is step number one, brother? Step number one is you need to idealize the structure. The structure itself is idealized. Okay, so there is no need of any other thing. So maybe I can step number two, maybe I can say at each and every joint you need to work out the distribution factors. Maybe I can say I can use the tabular form, maybe joint, maybe I can write here, one second, highlighter or eraser. Joint I can write here, joint, this is joint A, joint B, right? And C is not a joint, it's a free end, so please be aware of that. So when it is joint A and joint B, now in this at joint A, how many number of members are there? I can write member I can write as clearly member AB, and at joint B it is BA is one member is there and another member is BC is there. So you need to work out distribution factor. What is the distribution factor? So maybe I can write here. Distribution factor of member AB. Distribution factor of member AB is 1 because only one member is there from joint A. And coming to distribution factor of member BA and BC, right? So for member BA and BC, what are the values of these distribution factors? So coming to BA and BC, you need to work out, right? So can I work out here K distribution factor of BA? How I can work out distribution factor of BA? I can say stiffness of member BA by sum of the stiffness of member BA and BC. Stiffness of member B is the near end, A is the far end. Far end is fixed. When far end is fixed, I can write I by L. L is 4. Far end is fixed, I by L, I by 4. This is B is near end, C is far end. Far end is free. When far end is free, the value, the relative stiffness or maybe absolute stiffness, I can directly treat as 0. Say already mentioned. So here it is 1. The distribution factor for member BA is 1. Right? Maybe I can clearly write here. Clearly, yes, this is 1. So when the distribution factor of member BA is 1, the distribution factor of member BC is 0. How I can say that the distribution factor of member BC is 0? Sum of the distribution factors of all the members meeting at a joint is 1. So at B there are two members, BA and BC. For BA itself it is 1, so for BC it is 0. That means physically what is the understanding is, if you apply moment M at joint B, the total moment is taken care by member BA completely. Member BC will not take any sort of moment in distributing the moment. Okay, that's what is the physical understanding. Now what next step is, step number 2 is also over. Step number 3, fixed end moments. What are the fixed end moments? So fixed end moments, at each and every joint fix and work out the moments. So what are the joints? A is a joint, B is a joint. So at A, at B and at C. So at C it is it's a free, it's not a joint. So if it is if it is 30 kilonewton and this is 1.2, in such case the fixed and what this is 120. Because of 120 kilonewton, what is the fixed end moment in A, fixed end moment in BA, AB? You need to work out. These are the directions of fixed end moments, right? This is the direction of fixed end moment in BC. So can you work out what is the fixed end moment of MFAB? WL by 8. So it is WL by 8 is 120 into length. Length is 4 meter. 4 by 8. 4 ones, 4 twos. It is 60 and it is an anti-clockwise now, so minus 60. I can write fixed end moment in BA. It is clockwise and it is plus 60. And what is fixed end moment of member BC? At BC is just like a cantilever and it is 30 into 1.2. 30 into 1.2, it is minus this is an anti-clockwise moment now, so it is an anti-clockwise moment, so it is 36. When it is anti-clockwise moment, I should write it as minus 36, right? So these are the fixed end moments. And and after this one at exterior, interior, at exterior simple supports, I need to release the moment. When there is an exterior simple support is there, if I am releasing step number 4, whenever there is an exterior simple support is there, I need to release that moment. So what is the net unbalanced moment at B, which is plus 60 minus 36, and it is plus 24 is the answer. So I can say here I am releasing or unlocking the end moments, and or I can say simply I can say balancing also, balancing the moment. To balance the unbalanced moment is plus 24. So physically at B we are keeping an externally applied moment of 24 minus 24. When I apply minus 24, minus balancing and distribution, when I say minus 24 is applied physically, that minus 24 will go directly to member BA, because based on distribution factor BA, it is distribution. What is the moment in member BA? When I apply moment M at B, that is moment at joint B into distribution factor of member BA, which is minus 24. So minus 24, and here it will become 0. After this balancing and distribution, I can say necessary carryover will also be done. What is the carryover? If B is a near joint, carryover moment will happen to the far end. Far ends are C and far ends are A. At A it's a fixed end, so at fixed end, at fixed end, carryover moment is possible. It is half of this one, which is half of this minus 24 is minus 12. I can say simply here carryover, right? Whereas carry over to the end C is not possible, because end C because if you take end C, it is a free end where there is no moment, right? So if you take directly, what is the moment at A, what is moment at point A in member AB? Minus 60 minus 12. So it is can you work out modified fixation in minus 72? I can write here minus 72, and here plus 60 minus 24, it is plus 36. Here it is minus 36. And these interior joints, whatever you call this interior, if you take B as the interior joint, that interior joint moment is also balanced, and the moment at A is minus 72. So directly I can write here at moment at A, MAB, and it is minus 72, means the moment is in anti-clockwise fashion. So you can pick option B for Boston is the correct one. This is how you can do, brother. Okay, so this is one way. Another way, some people will say like, sir, what is the another way that we can do? Another way also we can do. Can I rub the screen? The answer is B for Boston. In this way you can do. Maybe another way, I am idealizing the structure. What is the effect of overhang? The effect of overhang should be shown as a moment on the joint. Maybe I can show. This is 30 into 1.2. This is how 30 into 1 point. This is anti-clockwise. This is 36. Now this is clockwise 36. This is clockwise 36, and here this is 120 kilonewton. So this is 2 meter, and this is 2 meter, right? So in another way also you can do. In another way is the same structure can be taken as a combination of this one and a combination of this one, right? So maybe here, when this may be, this is the point where the moment is applied. Now this may be the near end, this may be the far end. When far end is fixed, how much amount of moment is carried over to the far end? This is 36 by 2, 36 by 2. I can write 36 by 2, right? And here simply, if you are able to work out the moments here, the problem is over. So how to work out the moments here? Maybe I can say, when you had fixed, this is here, this is directly here. I can say, 1 second. When you had taken this as fixed and fixed, by that time this is already WL by 8, which is 120 into L. L is 4, W L by 8, which is 60. But here the moment here where it is also fixed, then this is also 60. But the moment at this B should be 0. That's the reason why I should apply an anti-clockwise 60. When this anti-clockwise when this is anti-clockwise 60, this is definitely 60 by 2. So if you add up these two, the answer moment at A is 120. This is already 60, anti-clockwise 60, so minus 60. This is anti-clockwise 60 by 2, minus 60 by 2. And here at A, I am just trying to use superimposition, so superposition principle. What is the net moments at A? I am trying to add up this and this, which is 36 by 2. It is clockwise and a plus 36 by 2. So it is minus 90 plus 36 by 2. If you add up, definitely it is equal to minus 72 kilometer. In this way you can work out. Even this is the another way, okay, without using any sort of tabular form. Some people will cry at me like, sir, why you are using here this is step number 3. I am direct, this is anti-clockwise 60, anti-clockwise 60, these are step number 3. When because of when the joints are restrained, these are fixed end moments. But actually at B it is a roller end, so I need to release that moment. If I release that moment, I am applying an anti-clockwise 60 here. And when this is anti-clockwise 60 at this end here, at the far end, how much amount of moment is carried over? It is 60 by 2, that much moment is carried over. So I can write 60 by 2. So this I had done. This there are no interior joints here. Also there are no interior joints. The final moment that we got directly are directly the final moments. So adding up this 60 minus 60, this is minus 60 by 2, minus 60 by 2, this is clockwise 36 by 2, which is plus. So minus 60 plus 36 by 2, this is the moment at A. That's what moment at A. In member AB, to be frank, I should write MAB is the answer. How I can write, and it is minus 72, right? This is how you can get B for poster. So moving to the next question, brother. I hope you are able to see this question. If a point load is acting, if a point load is acting at the midspan of a continuous, if a point load is acting at the midspan, right, right. Okay, Shubham Roy, Vasant Sai. Okay. Right, right. Okay, Shubham Roy, Anand Divedi. Okay. So, okay, can you see this question? Right. If a point load is acting at the midspan of a fixed beam, I hope you can take a fixed beam. If a point load is acting at the midspan, maybe that point load I can take it as P of a uniform cross section, that is flexural is same, produces a fixed end moment. What are these are producing a fixed end moments of, this is producing fixed end moments directly. This is 60 and this is 60, that's what. And that fixed end moments for this one is PL by 8, right? They had given that PL by 8 is 16. And if the same total load is spread uniformly, maybe I can say, when it is spread uniformly, I can say this is P, it is total. If I say in terms of UDL intensity, it is P by L, capital P by L is a small p. This is how you can write. Uniformly distributed load is total load by length, right? P is the total load divided by L. In this case, what is the, in this is the case, if the same total load is spread uniformly over the entire span, it will produce fixed end moments. What is the moment that is generated, right? That is the question. So I hope you can see in this case, which is if this is P, which is equal to W, which is equal to capital P by L. The answer is WL square by 12. So it is WL square by 12. W is capital P by L into L square by 12. That is the question, which is capital P L by 12 is the answer. I want capital PL by 12, whereas capital PL by 8 is 60. So what is the answer of capital PL by 12? So 60 into 8 by 12, right? 60 into 8 by 12, how much is the answer, brother? 12 fives are 60, 8 fives are directly 40. You can write, this is how you can keep this answer C, which is 40 kilonewton meter, right? 40 kilonewton meter, we can directly write that. Is it okay? Right, can I move to the next question? Moving to the next question. So find the moment in the AB of the figure. Find the moment in this member AB. Find the moment in member AB. So there are expecting moment at point A indirectly. What is MAB? Moment at point A in member AB. This is how we can write, right? Isn't it or not? Yes. Okay. So let us work out that moment at point A. Find the moment at point. So there may be some moment is there, maybe clock or anti-clock. We will talk that later. Find the moment in AB for the following figure shown, in which distribution factors at joint B are given in boxes. These boxes, these are the distribution factors that were given for the members. There is no need to work out step number 2. Step number 2 was given. Step number 1, step number 2 is directly given. And this loading, this maximum loading, here it is 50 kilonewton per meter, right? So if you please excuse me, can we work out this stuff? Can I work out this one? I hope yes, we can work out this, right? Right. So right, anyway, I hope we can easily work out this stuff. Yes. Okay, now working out. I hope you can see this. This is these moments here are 5WL square by 96. These moments here are 5WL square by 96, right? It is 5 into W is 50 into L is 20 square by 96. Okay. Mm, 5 into 50 into 20 square by 96. The answer here, these moments are 1041.667. This is 1041.667. So the unbalanced moment at B is definitely the unbalanced moment at B is here the moments are, this is 0 and here the moments here at a 0. Directly pictorial view I am using. So there is an unbalanced moment of there is an anti-clock of 7041. To work out this one, so physically at point A I need to apply 1041.667. if I apply that one, right, how much is the moment that is carried over to member BA? How much is the moment that is carried over to member BC, right? This is clockwise. So in I can write MBA. I can write MBA. I can write, which is 1041.667 into 0.457. This is in MBA. If I take the free body diagram of member BA, right, 104 into 0.457, it is 400. There is yeah, Shashi Komet Reddy. Hi Shashi, how are you? Right? Hope you are fine, Shashi. Right? Yeah. This is 10446667. This is this is sorry. I should one second. Erase. Let me erase this. So maybe I think like instead of doing with the help of a tabular form, okay, let me work out this with the help of a tabular form. Maybe this is AB member, right? Right. This is member AB, uh, member AB. This is BA, BC, CB, and fixed end moments. These are zeros, and I can say here it is 5 WL square by 96. Now 5 into W is 50, L square is 25 WL square divided by 96. So here it is minus 1041.667 plus 1041.667. These are fixed moments. So after that one I need to balance this one. That means this is clockwise. So here I need to release the moment at C. That means physically I need to apply a moment minus 1041.667. This is balancing and distribution. After balancing and distribution, carryover should also be there. Carryover will happen to the nearer adjoining support, which is here. So it is minus 1041.667 by 2. So it is minus 520.833. So if you see here, what are the modified moments? I am expecting answer from Shashi Komit Reddy. Can you give me this answer, brother? Right. Maybe I can say modified moments here 0 0. Maybe I can say 520.833 plus 1041.667, right? It is minus 1562.5, and it is 0. Now you should understand the unbalanced moment at B is minus. So that means physically or practically I should apply a moment of clockwise 1562.5. Out of 1562.5, okay, how much amount of moment has gone to member BA? So it is 1562.5 into 0.457. One second, into 0.457. So maybe 1562.5 into 0.457. So it is 714.06. That is bending moment at B. Bending moment at point B in member BA, but they are expecting bending moment at point A in member AB. So bending moment at point B, bending moment in member AB is equal to 714.06 by 2. So it is 714.06 by 2 in the sense 714.06 by 2. It is 357.03, and it is clockwise in nature. This is clockwise, this is anti-clockwise. This is clockwise, this is anti-clockwise. Sorry, I forgot to give the directions, and I got this as directly as clockwise fashion. You can see option C is the correct answer. Directly you can pick without any disturbance. Directly you can do, right? So just you need to do the procedure. Maybe after you got acquainted, generally there is no need of any of this tabular form. I just use it to work out modified fixed moments. After that one I just used this pictorial view. How you understood the unbalanced moment is minus 156.2. The balance to balance it one I need to apply a clockwise a plus 1562.5. I applied that moment physically at B. If I apply a moment physically at joint B, the moments to the associated members will be taken care based on the distribution factors. So based on the distribution factor, this is the moment and this is the distribution factor for a AB member. So like that I had worked out, and they are expecting only for member AB. Now I had only shown that in member AB. Similarly, you can show the same stuff in member BC also. This is how, I mean, this member is 1562.5 into 0.542. This is not required. Okay, so directly you can pick option C. Is that okay, Shashi Komat Reddy? Vasant Sai? Can I move to the next question? Right? Moving to the next question. So I can recommend you guys, like you can subscribe to Let's Crack Gate and ESE channel. When you subscribe to Let's Crack Gate and ESE channel, so many free content will come to you. And as the subscription price is also going to get hiked, so I can recommend you guys, like, use this code BD10 and get subscribed to the paid course. When you had taken the paid course in detail, we will teach you for all the concepts, and so many benefits are there for the paid course. And the paid course will happen in the app, right? So can you see this question? Shashi Komat Reddy, can you see this question? Right? Calculate moment at A. Can you work out, calculate the moment at A? What is the maximum bending moment at A? How to calculate that? That bending moment at A, maybe the bending moment at A they are expecting. So this is how the structure is given. So whenever there is an overhang is there, try to, I mean, the best way to deal this overhang problems are, try to convert, idealize the structure, try to convert this overhang load as moment on the joint. So this is W into A, that is WA is the moment in the member. So the direction of moment on joint B is clockwise, which is in opposite direction. Right? Maybe I can directly show here in this way. This is A, this is B, and this is directly, this moment is clockwise W into A, right? Now what is the moment? At least right now you please tell me what is the answer of that moment at A. So this is just like near end, and this is far end. What is the name of this structure? It is idealized structure. So a moment of m of magnitude W into A is applied at the near end. When the far end is fixed, how much amount of moment is developed at the far end? So what is that answer? When the far end, the moment that is developed is in the direction of the applied moment at the near end, and the value is half of the moment applied at the near end. This is m, this is m by 2, which is equal to WA by 2. So the answer for moment at A is definitely moment. I can write MAB, it is equal to WA by 2, and this plus means because it is clockwise in fashion, and this is how I can write, that is WA by 2 I can write. Is that okay? Can I move to the next question? Next question, right? This is the next question. So here also the question is, find moment at fixed end A. So can you work out this moment at fixed end at A? So how to work out this one? The structure itself is an idealized structure. Step number 2, at each and every joint you need to work out the carryover moments. I mean, not the carryover, you need to work out the distribution factors. Distribution factor at A is 1 because only one member is there. Distribution factor at B is also 1, right? Because only one member is there, which is BA. If this is the case, step number 3 is take this structure and restrain the structure and find out fixed end moments. When I find out the fixed end moments, right, this is the direction of, these are the fixed end moments. One is at these ends, it is WL square by 12, this is WL square by 12, right? And after step number 4, wherever there are exterior simple supports are there, at that exterior simple supports like at B, release or unlock the moment. To release or unlock the moments means making the moment at B as 0. How you can make the moment at B as 0? Right now it is clockwise WL square by 12, so I need to make the moment at B as 0, means I need to apply an anti-clockwise moment of WL square by 12 at joint B. If I apply WL square by 12 anti-clockwise moment at joint B, that moment is taken care by member BA. Now the moment, the magnitude of moment WL square by 12, whatever may be that I am applying, that is that point is taken as near end. Near end is the point where the moments are applied. Okay, so when a moment is applied at the near end, so what is the moment that is developed at the far end? And this is far end, when the far end is fixed, when the far end is fixed, and this is far end is fixed, what is the carryover? I mean, after you balance and distribute the moment, step number 5 is carryover. What is the carryover moment to the nearer adjoining support? The nearer adjoining support to support B is A. So at A I need to carry over the moment. That carryover moment is half of the applied moment. If this is M, which is WL square by 12, which is WL square by 12 divided by 2, which we call it as m by 2. Now after this one, there are no interior supports. All A and B are exterior supports only. So what is the moment? There is no need to check for balance of there is no need to check for moment equilibrium condition at interior joint. There is all the joints A and B are exterior joints, so there is no need to check for moment equilibrium at any of the joint. So I can say what is the moment at A, MAB. If you see, this is anti-clockwise of WL square by 12, and it is WL square by 24. I hope you are able to see two moments finally. This is WL square by 24, WL square by 12. You need to add up because these two are in same direction, right? So I can say clearly like WL square by 12 plus WL square by 24, and I can say anti-clock. Or if you want to keep, you can keep minus, then it, and directly you can understand it's an anti-clock. So if it is the stuff directly, you can write this 24. So 12 ones 12 2's 24. So here directly you can write 3 WL square. So here it gets a WL square by 8. So directly the moment at A, directly we can pick is WL square by 8. In that way you can directly do. Of course the options I had stopped, but directly you can. This is an indeterminate structure, and this indeterminate structure has right now got converted to determinate structure after I work out this bending moment at point A in member AB, right? Okay, can uh, one second. Some people will also ask us, sir, okay, you had worked out what is the moment here. It is anti-clockwise, which is WL square by 8. After this one, because analysis means you need to draw SFD and BMD also. Now, how to draw that one? So, can you draw SFD and BMD after after you work out this? This has WL square by 8. Maybe yes, definitely. This is maybe A. This may be B. This reaction at A is called as, maybe I can write as VA. This reaction at B is called as VB, right? One second. Right. Now this is WL. Now can you work out these reactions to draw the shear force and all this stuff? Yes. If you are able to apply sigma m about point A is equal to 0. This is anti-clockwise. This is minus WL square, and about this point moment of VA will become 0, and VA into 0, and about this point A, this load is W into L. W into L is trying to rotate clockwise. W into L into this distance is L over 2. So I can write WL into L over 2. And about this point, this VB is trying to rotate anti-clockwise. So minus VB into distance is L. Length of this member is L. So if you work out this stuff, definitely bro, the value of VB is 3WL by 8. This VB is 3WL by 8, and it is positive sense, means the azimuth direction is correct. After this azimuth direction is correct, what is the answer of VA? The answer for VA, how you can work out? You can write sigma Fi is equal to 0. Total double, so the VA is WL minus 3WL by 8 by writing sigma Fi is equal to 0, right? So in such case, this answer will be the reaction of VA reaction of VA is 5WL by 8. This is the way generally how we will work out. If you are expecting me to draw the free body, if you are expecting me to draw the SFD, this VA is going up by 5WL by 8, and this is WL is coming down, so plus WL by 8 minus WL. The area of this UDL I had added up from A to B, so plus 5WL by 8 minus WL, it will move to 3WL by 8 minus, so it will go in this way, right? And from 3WL by 8 plus 3WL by 8 will go to 0. So this is plus and this is minus. This is how we can draw shear force diagram. Maybe the shear force diagrams and everything your teacher had already discussed with you in your strength of materials concept. This is the point where shear force is changing its sign, and the distance of this x value, this is 3WL by 8. Distance of this x value from B is x. Distance of this point where shear force is changing its side, from this side this is L minus 6. How to work out this x? I hope you can directly draw the similar triangles properties. This angle and this angle is one and same, so tan theta is equal to, I hope you can write 3WL by 8 divided by x is equal to 5WL by 8 divided by L minus 6. If you do this stuff, definitely you are bound to get this value of x as 3L by 8. So the point from this simple supported end, the point where the shear force is changing its sign is 3L by 8. At that point only bending moment will also be maximum, definitely, right? So if you are expecting me to draw the bending moment diagram, BMD diagram also, right? In such case, can I rub the screen here, right? Erasing all ink on this slide. I mean, this is how the shear force diagram. What is positive shear in my case? A shear force which will rotate the element in clockwise fashion is positive. A shear force which will rotate the element in anti-clockwise fashion is negative. This is how I can take the shear force positive sign convention, right? Okay, maybe just rubbing the screen. If you draw the bending moment diagram, this is how the bending moment diagram will. And the maximum value of bending moment, and this is maximum hogging bending moment. This is hog, this is minus or hog, and this is sag I can write, and this value is W L square by 8, and this maximum value of sagging. This maximum value of sagging, if you work out, definitely this value will be, of course, if you can work out at this point, is the point at this distance. This distance is x is equal to 3L by 8. At this one, this value will be 9WL square by 128. This minus and this plus. This is how you can work out, right? So moving to the next problem. Two symmetrical continuous beam with simple supports. I hope you are able to see. This is how the question is. Two span symmetrical continuous beam with simple supports were there. Two span symmetrical continuous beam with simple supports were there in this way. Second. One minute, bro, let me drink some water. Okay. This is the next question. A two span continuous beam with simple supports were there. A continuous beam is there and simple supported continuous beam. Okay. The question is very simple. Question is find the design bending moment, question number 1. And question number 2, find the total reaction at B. There are two questions for these problems, right? So can you work out this? Yes, we can work out this, man. So this is a two span symmetrical continuous beam with simple supports, and its degree of static inertia of this structure is 1, right? Now after you see this one, to find out the design bending moment, what do you mean by design bending moment? The maximum bending moment that is possible in the structure due to loads. Maximum bending moment developing in structure due to applied loads. I can say that. Okay. Okay. Now when we had taken in this way, now the question is how to find out this design bending moment. This is an indeterminate structure, so you need to follow moment distribution method. And coming to step number 1, the structure itself is idealized structure. Okay, I am taking the structure as it is. Maybe this is how the structure is taken, right? And I hope maybe if you take this, find design bending moment. I want to find out design bending moment. I just want to rub the screen. Can I rub the screen and can I do the problem, brother? I just rubbed the screen and I am using the structure directly. A, B, C. Right. Step number 1, idealize structure. The structure is idealized. Okay. Step number 2, find out distribution factor. This is A, B, C. For a joint A, only one member is the distribution factor. For AB member is 1. For joint B, for member BA it is 0.5. For member BC it is 0.5. It's a symmetrical structure. I hope symmetry is there. So because of that one, only two members are there. Na? Half and half. If you don't trust me, you can work out the distribution factor of BA separately and for BC separately, and you can show that. And step number 3, I just want to show the same stuff in terms of tabular form first. So coming to tabular form, fixed end moments. Fixed end moments, maybe I can say this is in AB, this is in BA, BC, CB, and it is a uniformly distributed load of W. Na? So fixed end moments here it is anti-clockwise fixed end moment. I hope when you fix all this stuff, this is anti-clockwise moment, this is clock, this is anti-clock here, and when you this is clock, so it is minus W L square by 8. Third step, plus W L square by 8, minus when BC it is an anti-clockwise now, so minus W L square by 8 plus W L square by 8. Step number 4, release or unlock the exterior simple supports. What are exterior simple supports? At A it is an exterior simple support. Maybe I hope you can see. At A it's an exterior simple support. At C also exterior simple support. So I can say balancing. When I balancing that one at A to make the moment as 0 in member AB, I need to I need to physically apply a clockwise moment here, because the unbalanced moment at joint A in member AB is WL square minus WL square, right? So practically I need to apply here plus WL square by 8, and at the same time I need to release or unlock the moments at exterior simple support C also. At exterior simple support C in member CB, WL square by 8 is there. To make that moment as 0, to release that moment, I need to apply minus WL square by 8. Okay, I had applied that one. After I apply that one, after this balancing, and I need to do carryover. Carryover will be done to the nearer adjoining support. What is nearer adjoining support of member of joint A? P. What is nearer adjoining support of joint C? P. So if I do here, it is WL square by, and at B it is taken as an interior roller support where it is rigid. So you can treat the joint B as fixed. So at A it is near end. This is far end. Far end is rigid or fixed, which is the half of the moment is carried out. WL square by, sorry, this is fixed end moments are not WL square by 8, brother. The fixed end moments are WL square by 12. Sorry, fixed end moments are WL square by 12. Right. So here when it is WL square by 12, WL square by 12, here half of the moment it is carried over means WL square by 12 divided by 2, which is WL square by 24. Here also half of the moment is carried over to the nearer adjoining member or member support, which is minus WL square by 24. And after I do here, I need to work out the modified fixed end moments, modified moments, right? Can I work out modified moments? The modified moments is, here it is 0 minus WL square by 12 plus, it is plus WL square by 12 plus WL square by 24. It is plus WL square by I can directly write as A plus WL square by 8. You can directly write, right, plus WL square by 8. Here it is minus WL square by 8. It is 0. So the if you take after this one, step number 5, step number 6, check for interior, check for moment equilibrium is satisfying or not exactly at the interior joint support. The interior joint is B. At interior joint B, whether moment equilibrium is satisfied or not. I hope you can see directly here that MBA plus MBC, right now MBA1 it is it should be 0 whether it is satisfying or not at joint B. One is plus WL square by 8, another one is minus WL square by 8. Adding up these two, it is 0. Yes, it is satisfying moment equilibrium equation also, so there is no need of balancing, distribution, carryover, nothing is required. The moments that we got right now are directly final moments. The moments that we got right now are directly final moments, I can say. So I can say these are the final moments. 1 second. It is WL square by 8 here, and it is also WL square by 8. So maybe if you please excuse me, I will show these final end moments here in this one. So can I rub the screen here first? These are the final end moments. Can I rub the screen here? Yes. So rubbing the screen, maybe. So the moments here, it is, this is clock, this is anti-clock here, because one is plus, another one is, this is WL square by 8 and this is WL square by 8. If you work out, this is just like that of a a propped cantilever with fixed end. This is just like that of that one only. And this moment is how much, brother? This is A, this is B, and this moment is definitely directly WL square by 8. When it is directly WL square by 8, when it is definitely a direct WL square by 8. Okay, now after this WL square by 8, you had this WL square. I hope for this structure you had already done this maximum bending moment. Maximum bending moments are exactly at this one. So if you want to show, this is how the bending moment diagram that is possible. And this maximum value of bending moment is, this is WL square by 8, and the maximum sagging bending moment maybe that is possible is this much. This value is less than that one. If you don't trust me, you can work out this. Maybe the reaction is called as RA, we can write. Maybe this reaction is this reaction we can directly write this as this reaction is definitely 5WL by 8. This reaction is 3WL by 8, and definitely if you draw this what I can say, if you draw this shear force diagram, brother, This is how it will be in this way. The same, this is symmetrical. The same half will be on the right hand side. This is 3WL by 8. Question is design bending moment. Question is find design bending moment. If I want to find out the design bending moment, I can do it this way. This is 3WL by 8 and this is 5WL by 8. This is SFD. Distance from this side you had already worked out in your previous problem. This distance from this side is definitely 3L by 8. If you are able to take up the area of this one, definitely the bend, this is the maximum bending moment, which this maximum bending moment will be area of this portion, which is half into base is 3L by 8 into 3WL by 8. Definitely you will end up with 9WL square by 128. When compared to WL square by 8, 9WL square by 128 is less. So the maximum bending moment, this is hogging bending moment, this is sagging bending moment. The maximum bending moment out of these two are hogging bending moment, which is WL square by 8. So like that we can mention this is the maximum bending moment, I can say, or indirectly I can say this is the design bending moment. Design bending moment. In this way we can work out. And this is about question 1. What is question number 2, brother? Question number 2, see here, the reaction from the left hand side span is 5WL by 8. The reaction from the right hand side span is 5WL by 8. What is the question number 2? Total reaction at B. What is total vertical reaction? Total vertical reaction at B. What is the total vertical reaction at B? This is 5. This is already, you know, this is 5WL by 8. This is 5WL by 8. So 5WL by 8 plus 5WL by 8, which is 10WL by 8. 10 small WL by 8. So column B is actually designed for axial force of 10 small WL by 8, and the column B, if there is a column is there at B, the column B shall be designed for a zero moment, because this is one is clockwise moment, another one is anti-clockwise moment. These two moments are nullified here, right? The same stuff. 10 axial force and column at B. So or the vertical reaction at B, the total vertical reaction at B is 10WL by 8, and these are the directions. One is clockwise and another one is anti-clockwise, na? Which is WL square by 8. This is W small WL square by 8. This is how you can understand. Okay, moving to the next problem, bro. I hope you are able to see this problem, right? Are you able to see this problem, right? Right. Okay, let me be back in a minute. 1 second, if you please excuse me, I'll be back in a minute. Right, bros. Okay, let me start. Okay, 1 second. Okay, for this question also, for this question, find this is A, this is B. For this question, find MAB. Pending moment at point A in member AB, they are expecting. So how you can deal this problem? So the same stuff. Uh, First, idealize the structure. The structure is idealized already. It is a simple structure only. Second one. What is the second one? Maybe I can say this is A, this is B. So if I fix on both the sides, uh, find out fixed end moment at AB. So maybe step number two. Step number one is idealize structure. Step number two is distribution factor. This distribution factor here it is one. The distribution factor of member AB BA is also one. So maybe I can say next one. Next stuff is I need to take the step number three. I need to work out the fixed end moments. When I work out the fixed end moments, W this is WL by 8, this is WL by 8. Step number 4, release or unlock the end simple support moment. The end simple supports are at B. So at B I need to unlock or release the moment. How I can unlock or release the moment at B? By applying an anti-clockwise moment of same magnitude WL by 8 in opposite direction. Okay, definitely the moment at B will become 0. So this is similar here. That means out of WL by 8, total moment is taken care by member BA. So what is the moment? This is maybe the near end. So after this balancing is balancing a distribution, what is the carryover? The carryover moment will happen to the nearer adjoining support. What is the nearer adjoining support? The nearer adjoining support is at the far end, which is at A. The far end A, the carryover is possible, and it is half of this moment M is applied. The moment that is coming here as carryover is half of that moment, which is WL by 16. So there are no interior supports are there, so directly I can say it has got what I can say this sub the I can say simply like the supports has got uh, uh, the structure has got there is no need to check for satisfying interior moment equilibrium equation. So the moments that we got directly are final moments. So here it is WL by 16 plus WL by 8, which is 3 WL by 16. So directly I can say here the moment at A MAB, the fixed end moment MAB is directly equal to 3WL by 16, and it is in anti-clockwise direction. And it is in anti-clockwise direction. Shake this. And it is in anti-clockwise direction. I can write 3WL by 16. It is clearly in anti-clockwise direction, right? So coming to the next question. For this question also, find design bending moment. So why we are interested only in design bending moments, man? Why we are only interested in design bending moments? We are interested only in design bending moments because because for the design of any structural element we will consider the maximum bending moment. That maximum bending moment that we can consider in the structure is called as design bending moment, right? That's the reason why being an analyzer we are always interested in design bending moments. right? This is W and this is W. And right now, what is the design bending moment here? This structure is just like this is at simple support here, at simple support C. This structure is as good just like that of at B. It's a rigid one, na? So this structure, if you can see, step number one, idealize the structure. Step number two, what is step number two, brother? Step number two is uh, step number two. The step number two is what? The step number two is you need to work out distribution factors, right? So working out the distribution factors directly first. Distribution factor here, it is 1 for AB. Maybe we can directly write the tabular form if you want. Distribution factor of AB is 1. Maybe I can say this is joint member. I can write this is AB, member BA, member BC, member CB. This is how we can write. After I write this one, right, now after member you can write distribution factors here it is 1, and for here it is 0.5, and for BC it is 0.5, for member CB it is 1, right? And fixed end moments are it here it is minus WL by 8. You try to fix at each and every support fixed end moments. This is plus WL by clockwise, minus WL by 8, plus WL by 8. Now after this one, you need to work out or step number 4, wherever there are simple supports are there, exterior simple supports, release the moment at the exterior simple supports. So when there is an exterior simple support is there here, release the moment here at exterior simple supports. Release the moment here at exterior simple supports means I can say as balancing and carryover. So balancing and carryover, how we can do that one? That means practically we are applying here uh, plus WL by 8 here, and here it is minus WL by 8. Then only the moments at A and C will become 0. Balancing is there, and the balancing and distribution is there. Carryover is possible to the nearer adjoining far ends. These are near supports. These are near supports. The far ends are at B. So this WL by 16 here also, this is W minus WL by 16. Balancing, distribution and carryover is over, and after that I need to work out modified fixed end moments, end moments, and this is minus WL by 8 plus WL by 0. This is plus WL by 8 plus WL by 16. So directly we can write as plus 3WL by 16. This is minus 3WL by 16, and it is 0. This is how we can do. And when we do in this way, definitely, right, when we do in this way, there are, what are the interior joint? The interior joints are B. At interior joint, definitely the moments are fine, the moments are balanced. The joint B is satisfying the moment equilibrium condition, right? Joint B is satisfying moment equilibrium condition. The moment that we have directly is the final end moment. So if you take, maybe this is A and this may be M, this is W. Let me write the value directly. It is 3WL by 60, 3WL by 60. This may be reaction RP1, this may be reaction RP2, this is RC, this is RA. So if you work out, the free body, if you work out the bending moment is maximum. Definitely the bending moment is maximum at this interior support B, right? So I can say the design maximum bending moment is definitely, I can say, which is 3WL by 16. And some people will not trust this one. Maybe they will say like, okay sir, we don't trust this one. The maximum bending moment is not possible at B, maybe under the point loads. If you want to check if it is at under the point loads, if you want to check, in such case you can work out these reactions RA and RB1. RA into distance L by 2, you will work out that moment will be less than definitely this 3L by 16, right? Like that you can easily understand for this one also, right? Next question. A simple supported beam of length L, a simple supported beam of length L and uniform cross section is subjected to UDL throughout. Uniform cross section is subjected to UDL throughout. UDL load is acting. Okay. Suddenly a rigid prop is placed at the center. Suddenly a rigid prop is placed at the center. The bending moment at the rigid support. So what is the bending moment? Maybe MBA or maybe MBC they are expecting. So this is just like you had already seen the bending. This is just like a fixed at B and at A. This length is L over 2. What is the bending moment in MBA? So this bending moment here in MBA, this is directly we can write as WL square by 8. So W is W, L is L by 2. This we had already derived. W L by 2 square WL square by 8. This is how we can work out. So in such case it is WL square by 2 2s are 4, 8 4s are 32. I can write WL square by 32 and it is hogging in nature. Because this moment at the interior moments, all the interior moments, the loading is purely downwards. The interior moments generally are hogging in nature and the value is WL square by 32. Right, we can directly write it is WL square by 32. Right. Right. Moving to the next question. Moving to the next question. Moving to the next stuff. So, I think for today it's almost like 4 hours. We'll tackle the syncing of supports and other, frames problems in the next coming class. Okay. Anyway, as the number of hours for today is almost 4 hours. Okay. So let me just uh, okay. So I can say like every day free sessions are happening in Let's Crack Gate and ESE channel. So please subscribe to this Let's Crack Gate and ESE civil channel, and so many free content will come to you directly every day. And I can say I already started a new Telegram group, and the name of the Telegram channel is Unacademy underscore Civil Engineer Tilak. If you press here using this link, you can directly come to that link. In that link, if you join to that Telegram group, we will have some discussions about your questions also, and maybe I can say like whatever may be the free content that we are delivering, that will also be visible here. If you come down to our Telegram group, this is the Telegram channel. This is the Telegram channel link, and I can say even if you are a serious aspirant of GATE or ESE, today is the last day before price hike. I can say I can recommend you to use this code VT10 to subscribe to get the paid course, to get the subscription. And I can recommend you like if you press the bell icon, all the future coming videos will be notified to you. So please don't forget to press the bell icon, brothers. And all this you are getting for free of cost. Now please say the same thing to your friends so that they will also get motivated, they will also get benefited, and they will also get this content for free of cost, right? So please make a thumbs up. Thank you very much. And for today this is the end of the session.